when the guys are editing it, they've got a little bit of leeway.
That works better. Yes, it does. Teams. There you go. Teams. Now let's share a screen.
I have faith.
I don't.
I've got the faith. Yay!
There you go.
We'll wait until 2 o'clock. I'll introduce myself and Hugo as the host, and then Hugo can give you a little intro, and then we can kick off. Hey to everyone that's just joined. Let us know in the chat where you're joining from.
Dublin by way of Lincolnshire.
I've asked everyone where they're all from. We'll see if they... Oslo, Norway. Excellent. We've got people joining now, so we'll give it another minute or so before we do a kickoff. People will be transitioning between streams. Croatia, amazing. Love Croatia. Bucharest in Romania. I really want to visit Romania. Amazing architecture.
I definitely see familiar faces, or well, familiar names.
Yeah. Hearing everyone sharing where they're from, just like, I just can't wait to be able to travel again. Okay, right, it's 2 o'clock, so I'm just going to kick off because I'm sure we've got lots to cover. Okay, so welcome everybody. This is track 3. I am your host as well as Hugo. Hugo's online as well, and I'll let Hugo introduce the session.
Yeah. So hi everyone. Now we have Aidan talking about Trust No One security for service and data. So I hand over to Aidan. All good, Aidan?
Hey, good afternoon, everyone, or whatever time it is there. Greetings from the Midlands of Ireland. My name is Aidan Finn, and I'm a Microsoft MVP, or most valuable, or Microsoft Valuable Professional, with the Azure expertise. And as Hugo said, I'm going to talk to you today about implementing Trust No One security for services and data that you're running or hosting in Microsoft Azure. I am the owner of a company called Cloud Mechanics, and that's a company that I started a few years ago to write and deliver my own Azure training. So I make a mockery of mock and focus on real world stuff that I've learned from implementing solutions for customers, whether they're small, medium customers, or as I do now with Innofactor Norway, with large customers. So with Innofactor, I'm a principal consultant, and I work on Azure infrastructure. In fact, in track 2 at the moment, my colleague Damien, who's my teammate and one of my co-product owners, we work on a virtual data center solution for governance and security for large enterprises in the Nordics, actually, not just Norway. I've been working in IT since '96, so I started off as a dev. That finished pretty quickly when I got bored of that and became a consultant. I've done sysadmin and training ever since 1996. And you name the infrastructure type stuff, I've done it, except for networking, which is funny because I'm the Azure networking guy at work. But I'll explain that a little later. You can find me blogging on aidanfinn.com. My employers, Innofactor, you can find them on innofactor.com. My own company is cloudmechanics.com. And you can find me on Twitter as @Joe_Elway. And speaking of cloud mechanics, I have written a new course. It's basically a day-long version of this session. This session is very condensed. There's not much time in 45 minutes to an hour to actually delve into some of the detail that you need to do here. In fact, there's topics in here I could quite happily spend 2 or 3 hours on just alone. But there's a conference running later this year called the European Cloud Conference, and they have sponsored a bunch of day-long training courses, which attendees can register for, and a lucky 20 people will get to attend those classes for free. So you can learn more about that on europeancloudconference.com/Azure Masterclass Series. My class is running on June 19th, and it's online, and it's free for those lucky 20. So, infrastructure and platform, because when you hear Azure network security, you're going to think, ugh, virtual machines. I'm not doing virtual machines. I'm focusing on the platform in the future. And you know what? That's perfectly sound plan. It's an ideal plan. It's not necessarily realistic for everybody, but it's an ideal. But the reality is there's always a network. Whether you see it or not, there is a network. And you have to understand that when you're trying to architect security for your services, governance for your services, or for your data. Those networks are there to provide connections to and from the internet, between components of your services, and potentially to your on-premises environment as well. Resources that we typically talk about, well, obviously virtual machines, but things like app services, Azure Kubernetes Service, Logic Apps, and pretty much everything else, they're all running on a network, whether you see it or not. And increasingly, we're connecting them to virtual networks or networks in Azure that we can see and that we create and we control. And we do that to take control. We want to manage the flows. We want visibility and logging. We want to limit who can see our data as it's moving from point A to point B. We want to be able to log that and audit that. We want to be able to block outsiders or people who we aren't working with, like our vendors or our customers or our partners. So we need a control of all that. So that means having to implement networks and connect even platform services to these networks and data services to these networks. Monitor everything and get alerts on any threats or any even break-ins. The essential term I want you to remember today is microsegmentation. Now, this is nothing new. This is an old term. However, it's coming back again. If you think about network security, how does it typically run in a physical data center? Well, the network admins put up some expensive firewalls at the edge of the data center where the internet comes into the building, and then that's typically it. Maybe they might spread out and create these things called secure zones, and that's a special term in Norway where I work. But that's it. They don't actually break it up very much. In fact, an awful lot of the customers that I deal with, and these are large enterprises, and for many years I've seen this, they don't firewall the VLANs or the virtual networks in their on-premises data centers. They instead just have this flat open network. They even turn off the Windows and the Linux firewall. And it's great for things like WannaCry and other pieces of malware that get onto your network and suddenly, bang, they're across the entire network. And that's why hackers are able to get from penetration to complete ownership in 7 minutes these days. 7 minutes. A couple of years ago, that was a day. And now it's 7 minutes. So now what we are supposed to do is implement security right down to the individual workload and even between tiers of the workload. So your web servers, your functions, your databases, all those things should have their own network security and only allowing communications from the appropriate clients or servers and only for the correct protocols and port numbers. To implement security correctly in Azure, we do have to get back to basics. Even if you think you know Azure networking, you probably don't. And that's the reality. I deal with this all the time, even in my previous role where I worked with Microsoft partners and getting them up to speed on Microsoft Azure. A lot of them thought they knew Azure, and as it turned out at the end of a training course, they'd come up to me and say, yeah, it turns out we didn't really know Azure. So I'm going to start off, and I've already told you this. I am not an on-premises network guy. I've never been that person. I was always the Windows guy and the System Center and then the Hyper-V guy. I have never created a VLAN in my life. And you're thinking, why am I listening to this guy about network security? It's because I know Azure networking really, really well, and I know how to secure it really, really well. I've become the Azure networking guy at work. I'm the guy that people come to when they've hit problems. What I have found is the people who do best at Azure networking are, funnily enough, the people who didn't really do networking in the on-premises environment. And the people who do worst at Azure networking are the people who are network admins. So I typically, when I'm dealing with a customer and I'm talking about this stuff, I can see the server people just grabbing the information I'm sharing, and it's like, this all makes sense. And I see the Cisco guy going, no, 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 no. What do you mean you can't ping the default gateway? That makes no sense. And that's because Azure networking is software defined. It's actually built on NSX, which you'll find on other platforms, even VMware. It's an abstraction of a physical network. You're never working on the physical network directly. This is why you're able to implement your own networks through the self-service portal. You could never do that with a physical network. You don't even see whatever VLANs may be there, even if there are VLANs in the Azure network, who knows? You're working at a completely abstracted layer, which means you can have your own network range, which is completely the same as someone else. It doesn't matter, because everything is abstracted and converted and switched and encapsulated. There is no default gateway, even though there's a default gateway. It's not an appliance. It's not something you can ping. You'll see that with other things like load balancers and all that sort of jazz inside the Azure fabric. These things do not physically exist. Like, the default gateway will not respond to any sort of ICMP. You won't see it in traceroute. You won't see it in ping. It is a fabric function. It's a form of routing. And you will see that with the Azure Load Balancer as well. There are different scenarios where we use virtual networks. So the obvious one is virtual machines. But then when you start looking at, okay, I want to do PCI DSS and I want to use app services and stuff like that, well, you say, well, I'm going to use the app service environment, or the isolated tier of app services. And those are VNet integrated services. And you'll see things like the higher tiers of API management and SQL managed instance, where these are all things that explicitly connect to a virtual network, have a private IP in that network, and you put it behind a firewall. But then there's less obvious scenarios. And in fact, there's even a new gray area, which I'll talk about later. The less obvious scenarios are where you are using pieces of the platform that happen to use virtual machines under the covers. So if I'm using Azure SQL, just plain old-fashioned Azure SQL, next, I got myself a database. No sign of any virtual machine. There's actually virtual machines under the covers. Even Azure Functions, which are referred to as serverless computing, there are virtual machines under the covers. And these things require virtual networks, and there is some level of communication going on there. So you have to keep that in mind when you're architecting your services. And when we're dealing with virtual networks, one of the security features we have in there is distributed denial of service attack defense, or DDoS. And this is a threat to businesses of all sizes. In fact, the only DDoS attack I've personally ever seen was against a small startup. And it went on for 3 days with a rented botnet. The attackers, they can be state-sponsored, they can be professional criminals. And in the case that I saw, it was a botnet that was rented. So an amateur with a credit card, you can go look at a YouTube video that tells you how to do this, go online, rent botnet and attack someone. And send them an email saying that if they pay the ransom, you'll stop the attack. And you'll see that stuff going on out there. You don't have to be one of the big TV networks or political organizations or anything like that to be attacked. There are 2 tiers of defense with DDoS protection. So we have the basic tier, which everybody gets. Every virtual network has the basic tier. This is a simple best effort mechanism that's taking advantage of the scale of the Microsoft WAN, which is the 2nd largest WAN on the planet. And that's what Azure lives on. It's doing a best effort approach based on the nature of the traffic in that Azure region. It's not tuned to your particular service or your tenant that you have in Microsoft Azure. It's a free function, so there's no level of additional support with it if you do get attacked. If you have auto-scaling services and they happen to auto-scale as a result of an attack, there's no cost protection for that either. However, if you do see yourself as being someone who might be attacked, you should look at the standard tier of DDoS protection, albeit that thing costs nearly $3,000 a month to turn on for up to 100 IPs, or public IPs. You would typically turn that only turn that on in the virtual networks that do have public IP addresses, because that's where it's only a benefit. And the standard tier does include things for cost protection of scale out. It is tuned using machine learning to your particular network. Now, the wrong thing to think here is, right, I'll turn that on when I get attacked and that'll be cool. No, because the machine learning takes approximately 2 weeks to learn the patterns of your virtual network and the spikes and the falls to understand what's an attack versus what's not an attack in terms of volumetric attacks. So you will want to turn this on in advance of the attack. So you really do need to expect an attack, or it's something that you say that if I am attacked, it's going to cost me an awful lot of money, and I can afford that, nearly $3,000 per month of insurance. And there's a lot more features to it as well, including advanced support who will kick in the event of an attack and help you tune the environment and tune the protection to mitigate that attack as well. And DDoS protection, it protects your public IP addresses. So we do need to talk a little bit about public IP addresses. The default behavior in Microsoft Azure and any cloud is everything's just public. That's just the way it is. If you go next, when you're creating a VM, once upon a time in the Azure portal, every VM got a public IP address. Now think about that in your on-premises environment. Would you do that with every server? I hope not. Would every server have a public IP address? Sounds a bit stupid, right? It's a huge attack surface that you would have to protect. And we do the same thing with platform. We go up and let's slash out some SQL databases, some Cosmos DB, and some app services. Everything's public. Yeah, everything's public. It's a huge attack surface you now have to protect. So we should be limiting that attack surface, only making things available through a small number of public IP addresses, where we've got the security mechanisms in place run by the people who understand security. Worst person to run security in my mind is a dev. And because the dev isn't focused on that stuff, the dev is focused on getting the business functionality up and running. They don't understand things like security and governance and compliance. That's not their core skill set. The security people should be running that stuff in a central point and making the services available through their secure mechanisms. So you can do things like using Azure Policy to limit the ability to create public IP addresses, for example. And then we can implement a basic layer 4 security using network security groups. And network security groups are a free form of transport layer or layer 4 firewalling. So we can create firewall rules for TCP, ICMP, and UDP. This is done using a resource called a network security group, or an NSG. And we associate that with a subnet. Now, earlier on, I was watching a pretty good session on Azure Security Fundamentals, and the speaker was talking about using Security Center. And there are merits and demerits to using Security Center. One of the negatives is it will give you some advice that's actually incorrect based on product group best practices. And one of those is how we deal with network security groups. Security Center will advise you to implement security groups with every NIC of every virtual machine. And that's crazy talk. Best practice from product group is one network security group for every subnet. And don't reuse network security groups across subnets. So each subnet has its own individual network security group. And that can control the inbound flows and the outbound flows as they hit that subnet. And that includes traffic in between services that are connected to that subnet as well. Typically, I only configure the inbound rules because I handle the outbound rules a different way, and we'll have a look at that later. Inbound rules, there are some default rules in there, so everything from virtual network is allowed in. Now, virtual network in that case has an interesting definition. Virtual network means, yes, everything in my virtual network that I created, but also every virtual network that is paired with my virtual network, and every other network that has a private connection across ExpressRoute or site-to-site VPN. So if I'm trying to do microsegmentation, using these default rules is bad. So I always override them, and you'll see that in an example in a moment. You'll see things like allow load balancer in. So that's the probe from the load balancer in the fabric, using a fixed public IP address, which begins with something like 168 as a source, and deny everything else. But that deny everything else is pretty useless if you have a complex network, and you end up having to implement your own deny everything else. And then we have the outbound default rules. You have to be really careful with that, because especially with virtual machines, because you're going to have lots of these extensions in Azure, like Azure Site Recovery, Log Analytics extensions, etc., which are all going to try to communicate with Azure. And if you haven't implemented the rules to allow those communications out, you're going, oh, I'm going to block everything that's not anything to do with my service. Then all those management features are going to stop working. So you have to really understand everything. This is why I like to do that at a central point. And I control my outbound flows at the firewall, at the hub of the network, rather than on the NSGs. And the rules are pretty simple. If you've implemented Linux or Windows rules or any basic firewalling, the rule configuration and setup is pretty simple. The trick here is to be as precise as possible. And as generic rules at the top, precise rules at the bottom, and then finally a deny rule that blocks everything. So you have your priority to order your rules, a name that's friendly. Use a good naming standard that describes what the rule actually is and what it's controlling. Your port and protocol to control the actual traffic flow, the source and destination, which can be a number of different things from IP addresses, CIDRs, service tags, which are abstractions of Azure services, so you don't need to know their IP addresses, and application security groups, which is another form of abstraction for virtual machines. So you can create tiers of a service using virtual machines, and in each tier, you take the NICs and add them to an application security group. So you don't need to know the IP addresses of the tiers, especially if you're doing auto scaling or you're using dynamic IP addressing. You just need to know the name of the application security group. It's also great for screenshots because you just take a screenshot and that's your documentation. And then your action, whether you're allowing or you're denying that particular flow. So I've talked about those labels, so we'll quickly move on. The service tag, yeah, I've also mentioned that, but I'll repeat it. Virtual network is dangerous, so beware of, trusting everything from virtual network and just assuming that it is that particular virtual network. As I said it before, it's peered virtual networks, express route connected networks, and VPN connected networks. So if you are going to implement microsegmentation or you're going to secure a service against every other virtual network that you may have, you will need to put in your own deny rule at the end of your rule set to block or basically override the default rule that allows everything from virtual network. And here we have a simple NSG rule set. So we have a web server subnet that has a set of rules, and you'll see rules 100, 200, and 300. As a packet comes in, it hits 100, and if it gets a positive match, it passes through. If it doesn't, it goes to 200. If it doesn't get a positive match there, it goes to 300. And there you'll see my deny everything else. I'm not waiting for the default rules to kick in because I don't trust them. I'm implementing microsegmentation. So I want to make sure that no matter where that packet comes from, whether it's another subnet in the same virtual network, another virtual network that's peered, or an on-premises network that's got an express route or VPN connection, if it doesn't get hit by rule 100 or 200, basically HTTP or HTTPS traffic or load balance or probes, then I'm denying it. It is not allowed into that web server subnet. Then on my back end here, I'll have another NSG, and I'll associate with that subnet. And you can see again, I've got rules there with a deny everything else. And you'll notice on my source and destinations, I'm taking advantage of application security groups. So I don't need to put in the IP addresses of each of the NICs. Instead, I use that friendly label that's an aggregation of each of the NICs in that particular service tier. Now, those examples are really, really simple, but the reality is you are going to need to put in lots more rules for your inbound. So things like allowing DNS responses, any other UDP type traffic that you may have that's connectionless, because the NSG is stateful and connectionless protocols don't have a state. So you have to allow the response. So things like DNS, radius, and that sort of thing need to be allowed. If you've got applications that are trying to push code in, or services that are trying to push code in or data in, you'll need to allow that traffic as well. If you've got third-party monitoring solutions, you'll possibly need to allow, the probes or whatever it is in. So understanding what your rule set is going to be tricky. If you're in a migration scenario, use the service map feature in Log Analytics. If you are troubleshooting and trying to understand, enable NSG traffic analytics. So that's where you're enabling the NSG flow logs, and then using log analytics to consume that data from a storage account, and then visualize it and put it into a database where you can query it using custom query language or Capable. That's really useful for troubleshooting. And I'm using that all the time. So that leads us to routing. And this is the most important thing you need to understand if you want to do network security in Azure. That is because routing is how you effectively cable the flows. If you think about a physical flow in a physical data center or computer room, you're using cables to control the flow from a server to a switch, and from a switch to a firewall, and from the firewall to a router. In a software-defined network, that doesn't happen because a packet goes from straight from A to B. It is a memory copy. So if a VM is communicating with an Azure SQL database, there is no flow from point A to point B to point C to point D by default. It literally is a memory copy from A to B that happens across the physical network of Azure and is encapsulated in that NSX software-defined network. And that's why you don't see a default gateway, because it doesn't actually get involved in the flows. It's just there to provide some sense to the guest operating system. So we have to plumb that network, and we do that using routing. Now, there's important things to know here. Again, software-defined network. So when a packet hits the network, at that point, the fabric takes over. It routes the packet. So no matter what routing you configure in the guest OS of a virtual machine or an appliance, the fabric always takes over when that packet drops in. All you can do is control which subnet the packet will egress on, and that's it. A route table will take over. And that route table exists whether you create a resource called a route table or not. Every subnet has one, whether you create a resource called a route table or not. And as it has a next hop instruction, where will that packet actually go to next? And there are a couple of laws in routing, and this is basically a description of how routing works. So the first law of routing is longest path first. If there are two routes that exist on a subnet to a possible destination, the one that's a best bit match will be used. So if I have two routes to 10.0.0.0/8 and 10.0.1.0/24, and I'm trying to send a packet to 10.0.1.4, the best bit match is that second path, 10.0.1.0/24. It's a 32-bit match. So automatically Azure will use that one, no matter what type of route it will find. The second law of Azure routing is there are three types of routes. We have user-defined routes. These are ones we explicitly create to control the flows from A to B. So my next hop from this subnet will be some other location or some appliance. That wins every time it is the most precise route. Then there's BGP, or Border Gateway Protocol. We see this always with ExpressRoute, sometimes with site-to-site VPN, and it plays a role in outbound route propagation from your Azure networks back to on-premises as well, and that bit's typically forgotten. User-defined routes beat BGP. BGP beats default or system routes, and these are the routes that are created when we turn features on in our networks. We don't typically see them or think of them. They're just the magic that happens automatically when we peer virtual networks, or we create a local network gateway and put some subnets into it. All this good stuff that happens just automatically happens across our entire virtual network architecture. Example of that is a very simple virtual network that has two subnets. Each of these subnets will have a hidden route table that you cannot see normally. There is a route to the virtual network itself. So if subnet 1 wants to get to another address that's in the address space of VNet 0, there is a route saying go directly to virtual network. So the memory copy will happen across virtual network. If I want to go anywhere else, so quad 0.0.0.0/0, it is told go to internet. Here's another interesting one. Internet doesn't actually mean the internet. Internet means outside this virtual network. So go to Azure and let it take over the routing from that point. So you're going outside this virtual network at that point. We have two virtual networks now, and we would like to peer them. And you'll see each of them has a route table. Each of the subnets has a route table. And we didn't create the route tables. There's no route table resources at this point. These are hidden route tables. And each of them has a route table saying, if you want to go to the other subnet, go via virtual network. If you want to go to anywhere else, go via internet. But I would like to peer these networks. So if I peer these networks, each of the subnets now gets a new default route that basically says, if you want to go to the address space of the peered virtual network, go via something called peering. Now the packets will flow over that peered connection automatically. We see BGP when we're doing site-to-site networking. So you always see it with ExpressRoute, and you'll typically see it in site-to-site VPN with large clients. If a customer has a small number of on-premises networks and they're doing site-to-site VPN, they may not want to configure BGP, and you might configure static routes in the local network gateway. However, BGP actually still plays a role because the gateway subnet will still propagate those statically defined networks, those statically defined on-premises networks in the local network gateway, to the rest of your hub virtual network and any peered spoke virtual networks you may have as well. But if we do have BGP from on-premises, the route will be propagated up through that site-to-site network connection to the gateway subnet. And you can see there is a BGP route there. Doesn't even need to be a route table created by us. This just happened under the covers in the fabric and is maintained by the fabric for us. That is then propagated out to other subnets that may be in VNet 0, but also to any peered virtual networks where we have configured gateway sharing. So at this point, we have a hub and spoke architecture. So each of the spokes, so VNet 1 and VNet 2, have use remote gateway turned on, and the hub, which is VNet 0 on the left, has gateway transit turned on. Now that BGP route is propagated out to each of the subnets in our spokes, but also the routes to those spokes are propagated back to the gateway subnet and the gateway and pushed back down to on-premises via BGP as well. BGP beats default. So now if I have a default route for 10.1.0.0/16 and a BGP route to the same location, the default route is deactivated in that fabric maintained route table, and the BGP route takes over. It becomes the active route, the winner. This brings us to user-defined routes. Now we want to start controlling the flows. Where do you start seeing these for the first time? It's when you implement a firewall. This is why I've spent so much time talking about routing, because we're going to start talking about firewalls and controlling the flow so they pass through our firewalls. And this is the only way you can do it. So this is why you must master routing. So to create user-defined routes, we will create something called a route table, and we will associate it with a subnet. And the best practices here are the same as with network security groups. If I create a route table, I will associate it with one subnet, and only with one subnet. It will not be shared across multiple subnets. And a common mistake is, and you'll see this in some of the Microsoft documentation, you'll see it in training materials, and it's a common enough mistake, and it's a misconception that if you create a user-defined route, it's the only route associated with that subnet. That is incorrect. The default routes are still there, the BGP routes are still there, and we have to manage those and control those and understand them to make the user-defined route work in the first place. Remember our first rule of routing, longest path first. Keep that in mind. So the routing components are pretty simple in the UDR. Have a human-friendly name, a CIDR destination, next hop type. So where do we want the packet to go? And if it's a virtual appliance like a firewall, the IP address of that appliance. Now, we have two flows to worry about. First is flows coming in from on-prem. We don't want to trust the on-prem network. We want to treat it as something that's dirty. It's potentially filled with viruses. So any flows coming in from on-prem via our VPN or ExpressRoute, we want them to come through our firewall. And to make that work, we have to put in a route. on the gateway subnet to say the next hop for any flows going to my destination networks is through the IP address of my firewall. And if you're doing a hub spoke architecture, which is what you likely are, if you are going to be paying up for firewall appliances or the Azure Firewall, then you have to put the address space of that spoke network in that route. So you can see on the bottom left, I've put in the address space of VNet1, and I've said that the next hop type is a virtual appliance, and it's the IP address of my Azure Firewall that's running in the Azure Firewall subnet in the hub. And that's my inbound flows, saying, right, everything trying to get to VNet1, it's going to pass through my Azure Firewall. My Azure Firewall allows it, it gets through. If my Azure Firewall doesn't allow it, it's now blocked. That's the only possible path at this point. Now I want to control my outbound flows. My problem with the previous configuration is I have a BGP route associated with subnet 1 in my spoke up in the top right. You see that BGP route? That says, hey, if you want to get to on-prem, you're going to go directly to Virtual Network Gateway. Now, the diagram may make it look like that the packets have to go to the Azure Firewall, but remember, in software-defined networking, packets go directly from source to destination. There is no hop in between. So right now, any packet leaving subnet 1 and VNet 1 will go straight to gateway subnet if it wants to get back to on-prem. But I don't want that flow. I want it to go through the firewall. So to make that happen, I have two things I need to do. First is I'm going to disable BGP propagation. How do I do that? I am going to create a route table resource and associate it with my subnet in the spoke. And in there's a setting called disable BGP propagation, and I turn that on. Now all the BGP routes that were coming from the gateway subnet disappear from that spoke subnet. And then I'm going to add a user-defined route or a UDR saying if you want to get to anywhere quad 0, 0, 0, 0, 0, /0, you will go through virtual appliance, and the IP address is the IP address of my Azure Firewall. Now any flows leaving that subnet with an asterisk will go through the Azure Firewall. Now you'll notice I said any flow, and then I put asterisk. Notice we still have default routes there. So there are still routes that are more precise and will still be used. And if you want to control those, you will have to create user-defined routes for those as well. Now, if you're clever with your architecture, you won't replace them and you'll actually use them. But I don't have time for that today. So how do we view these route tables? Well, the route table you create, the resource, that's simple, you just open it up. But what about the hidden route tables, the fabric ones? Well, right now, there's only two ways of figuring out what's in there. The first is you happen to have a virtual machine that's allocated and has a NIC on the subnet. You go to the NIC and you click View Effective Routes, and you wait about a minute or two, and then you'll get a dump of all the particular routes that are applied to that subnet. So the default routes, the BGP routes, and any user-defined routes. And you'll see which are active, which are inactive. So which ones have been turned off by the priority. So that's law number 2, where UDR beats BGP beats default. Then you have the other one, which is I don't have a NIC that's allocated. I have a subnet that's only got app service environment on it, or it's only got Azure Firewall on it, and I can't put a virtual machine on there. How do I figure out what the routes are on that subnet? Well, the answer is you have to learn how routing works and either figure it out in your head like I do, or start writing it down on maybe a whiteboard like Microsoft Whiteboard or a piece of paper and drawing out everything. Now, Microsoft have heard the feedback because I'm reminding them nearly every month, to be quite honest, the guy who actually owns this. I am pounding on them saying we need to be able to view effective routes on a subnet level rather than on a NIC. But right now, you need to be able to understand how routing works to be able to figure out what's going wrong on a flow. And this is really important if you're trying to implement firewalling. So, summary of my laws of routing. Longest path first, always wins. So the best bit match, no matter what the priority actually is, always works. If you have multiple routes that have the exact same CID or prefix or destination, then BGP beats default, UDR beats everything else. But if there are different priorities, then they remain active. That's when LPF kicks in again. And just because you can't see it, it doesn't mean it's there. there are always default routes. So even if you don't create a user-defined route, you don't create a route table, there are still default routes, and there's a good chance there's BGP routes there as well. And you need to understand how they get propagated around and turned on. Routing needs to work both ways. So a common mistake I see with people configuring routing is they configure how the packets get from the client to the server, but they don't configure the response. So you need to do that as well. And if you have firewalls implemented in Azure networking, if you have complicated flows and something breaks, it's always routing. The on-prem rule of troubleshooting networking is it's always DNS. It's always routing, unless it's DNS. Because still sometimes you can have name to IP address resolution issues in Azure as well, particularly in your, actually not just in virtual machines, but also in services where you're creating custom names. So I've seen that, for example, with API management for internal API or API consumption. So this brings us to the firewalls. Actually, routing is most of the architecture of firewalls, to be quite honest, especially if you're using Azure Firewall. Azure Firewall is just dead easy, and all of the engineering with it is actually routing. If you're using third-party firewalls, yes, the same routing. In fact, it may even be more complex, has to be implemented. And you have other things to deal with depending on the firewall appliance, its brand, and whether you're doing HA or not. But that firewall, do you need one? It's an expense. I've got these free NSGs. Do I need a firewall? And the reality is, if you're doing anything but the most simple Azure networking, yes, you need a firewall. You still need a central point that provides your network security. It's where I happen to control my outbound flows, because it's much easier to control them here when I've got my quad zero routes in each of my spokes. And I can also control outbound flows based on names depending on my brand of firewall as well here, rather than just doing simple TCP UDP rules. We can also use it as a form of as a router. So if I have multiple spokes, by default, spokes in a hub and spoke architecture can't route to each other. They need some sort of next hop in a hub to be able to get to the other spokes. So we can use our firewall for that function as well. So it's more than just simple firewall ruling. And as I said, we can also use this firewall for FQDN support for things like Azure SQL and websites and stuff like that as well. Now, what are you going to choose from your firewall? Are you going to go with the platform, which is the Azure Firewall, which is basically firewall as a service? No need to configure any VMs or NICs or HA or anything like that. It just happens automatically for you, automatically scales out up to 30 gigabits per second by default, and can actually be extended with a support call. No sort of OS maintenance or any of that junk. Or do you go with a third-party appliance? If you have this conversation with a network admin, they're always going to go, well, I run Fortinet on-prem, I want to run Fortinet in the cloud. And they expect they're going to get the same features in the cloud, and as it turns out, they just get basic firewalling. They don't get any of the other fancy jazz, and it comes at much reduced performance, much higher cost than they would have expected, etc. And there's a whole bunch of downsides, in my opinion, with virtual appliances as firewalls. As a cloud guy, as a person who wants to use as much platform as possible, the Azure Firewall is a much better choice. And one of the things I really like about this, and when you start talking to people who are working in DevOps or developers or people who want to use the cloud the way the cloud should be used in a mid to large enterprise, and you're doing infrastructure as code, which is what my colleague Damien's talking about right now over in track 2, you can manage the Azure Firewall entirely as code. So it's, yeah, I can use the central console in Firewall Manager, and I can use its policy engine. That's great. I can do simple resource management where I can configure the rules just inside the resource itself in the Azure portal. If I have only one firewall, that's fine. But I can manage this as code. I can store my code in GitHub or DevOps and pull it down in VS Code, tweak my rules there, do a pull request. The security officer can do a review on the merge, and if the security officer is happy, they approve the merge, and then the pipeline kicks in and then deploys out my rules. And I have a rollback mechanism. And you know what? It's also my CMDB, my configuration, my documentation. That's cool. And when you're able to do that and be able to do that, not just for your firewall, but for your entire infrastructure, Now you have one way of delivering configuration, management, and change control for your entire Azure infrastructure, not just for virtual machines, but for your entire service delivery as well. Instead of having some network person who spends 3 days trying to create a rule for you in a console or in a portal. So the Azure Firewall, really like it. It's got rules for doing network rules, so your simple layer 4 TCP UDP type rules. It's got application rules where it understands the FQDNs of things like web applications and SQL Server or Azure SQL. It's got a threat intelligence feature for looking at flows and seeing if they're going to or from dodgy locations. That one I only put in alert only mode. I don't let it block because it's using some third-party databases which aren't entirely the most reliable, especially when they start marking CDNs or content delivery networks as possible sources of threats, because then functionality that's completely illegitimate breaks. But it is useful to have that alerting there and be able to have a look at it. And if you have a look at what Paul presented on earlier on Sentinel, you might understand how you can start automating the resolution and investigation of those alerts as well. You have obviously all your logging, and we have Firewall Manager, which is in preview, which gives us a new central console and policy-based mechanism to manage many firewalls using a hierarchy of inherited policies. With different SKUs of the firewall. So the one that people are familiar with right now and the one that's generally available is the network SKU. But what's in preview right now is something called Secure Virtual Hub, which is a merger of the Azure Firewall with the Azure WAN Hub for SD-WANs. And it's not just for SD-WANs, because we can do ExpressRoute and simple site-to-site VPN and even end-user VPN at much greater scales than the traditional gateway can handle. It's a very interesting architecture. There's a lot of investment being put into this as well. The people behind it are really, really clever and really determined, and you can see the investment they've made, especially in the gateway functionality it's light years ahead of the typical virtual network gateway that people are using. It is still in preview though, so I wouldn't recommend it for production, but it is definitely worth keeping an eye on. I'll be trying to jump on it as soon as it's ready. There are third-party firewalls you can use. If this is something you have to use and you really want to use it and I can't convince you otherwise, well, pick and choose wisely. Some of the brands do a decent job and they have good documentation. I'm not going to name names here. Some of them are pretty awful. I won't name names here either. Cisco, excuse me, bad cough. And are worse than a bomb on your network, to be quite honest. And they should not be let on any virtual network in the cloud, whether it's Azure or AWS or whatever. Any brand that expects you to program the user-defined routes into their appliances so they can edit them on the fly, that's a red flag. It's worse than a red flag. That should be do not buy. And if they can't document their own architectures, don't touch them. And one of the brands I may have sneezed actually is kind of like that. You'll see simple architectures where some appliances can only support a single virtual machine with no HA. Not really good for any line of business service that you're going to depend on. You'll have some that split out into front-end and back-end subnets. To be quite honest, in the cloud and the way software-defined networking works, there's no real architectural or security benefit to this. And I don't know if we're sharing the slides or not, but we do have some extra detail on how the routing would configure in there. We're a bit constrained for time, so can't go into that too much. You can have HA clusters. Most will actually only do active passive, so you only get the throughput of one virtual appliance. There are a handful of brands out there that do active configurations and will support more than 2 nodes as well. You'll note in the architectures that the inbound flows must come through a basic Azure load balancer, and the outbound flows can egress through a standard load balancer. Some of the brands out there don't support a back-end load balancer, so you will have to create user-defined routes to go to an individual NIC and then change them. And that's where some of these brands require you to program the possible UDRs into each of your appliances, which are managed as individual appliances. So you have to double the amount of effort you do on an operational basis, which is just crazy stuff. in this day and age. So there's lots of stuff to have a look at in there. But my recommendation would always be Azure Firewall first, third party, like 10th. Those firewalls, they do basic stuff. They don't understand the application layer. They don't understand things like SQL injection attacks and malformed HTTP requests and all that sort of functionality. And this is where you get an appliance or a service or a resource called a web application firewall, or a WAF. And this is a firewall that's focused on HTTP or HTTPS traffic, where most applications are being built in the cloud today. So Microsoft are seeing a lot of customers who are saying, you know what, I don't need ExpressRoute or site-to-site VPN. I'm going to consume all of my services over HTTP or HTTPS, because that's all I'm going to build. And if I can get myself a low latency connection with an ISP, that will be more than enough for me. So this is different than your classic firewall. In fact, a lot of the time, with our customers, we're typically putting in this side by side with the classic firewall. There are a number of different options here. So you have third-party WAFs that run as appliances on your virtual network. You will have a third-party cloud service that can run in one or more locations around the globe. You know, there's a number of brands out there that offer that sort of functionality. And then we have two WAFs. Well, there's kind of a third sort of here at the moment, but we have two WAF options from Azure itself. We have the Azure Application Gateway WAF, which is an Azure Application Gateway is a layer 7 load balancer that understands HTTP, HTTPS, and we can add WAF functionality to it, and that runs on a virtual network. And then there's a service called Front Door in Azure, and this is a global service that reduces the latency between clients and your services running in Azure by getting those clients' flows into the Microsoft WAN using these 170 plus edge data centers that run around the world. That gives them a lower latency connection than just going straight across the internet to the Azure region where the service is running. And the WAF can run there as well. So basically block the bad stuff at the edge of the network before it ever gets in. So there's a few places we can actually run the WAF. You can run it centrally. So if it's a network-based WAF, you can put this on a hub network, and it's managed by the security experts. And every service that you're running in your spokes will be published through these WAFs, because there might be more than one of these depending on the scale of your network, the amount of traffic you're actually putting through. Now the security people are running this. Now that does have an impact on delivering new services, because there's a process that's got to be done, but realistically there's a process that should be always done to expose a valuable service to the internet. Or you can deploy that WAF with every single application, and this is something that we wouldn't typically recommend, because this is, you know, adding a public IP address to every service, which increases the size of your attack surface. I mean, security are now being handled by the developers, who are the wrong people, as I said earlier, to be doing that. And if we do centralize this, we can have better controls against things like DDoS attacks, etc. And we can protect these WAFs correctly using layer 4 protection, using network security groups as well. We typically don't put the WAF behind the traditional firewall. We put it beside the traditional firewall. If you are going to use the Azure WAF, and the current version is WAF v2, it's much superior to WAF v1. If you tried using WAF v1, the configuration of it, just setting up a web service, a simple publication of a HTTP or HTTPS web service could take you a couple of hours. And most of that couple of hours was waiting. The reality is no one wants to do that, and it drove a lot of people to third-party offerings. WAF v2 is a much higher SKU under the covers, and it's much better performance. It's a different architecture under the covers. It implements OWASP 3.1 at the moment. It does have older versions of OWASP. These are the rules that do your filtering and scanning and blocking and denying of HTTP, HTTPS traffic. And it's an open source set of rules. They look for things like SQL injection, malform requests, etc. It has key vault integration. So if you have an SSL certificates, we can offload the SSL decryption off to the application gateway and the WAF. And we can store those certificates securely in that virtual HSM. And we can use least privilege access, so the WAF can only read the certificates and access the certificates rather than anything else. And we do that using an Azure Managed ID. If we do enable DDoS protection on that virtual network that the WAF is running on, now DDoS protection runs at layer 4 and at layer 7 as well. And we get optional management. So realistically, if you're using WAF v2, you should be using something called a WAF policy resource. And this moves the policy management and the WAF configuration management to a dedicated resource. This gives you new features like better rules customization. So you can start turning off some of those false positives, especially for protecting things like API management, where you've got a lot of JSON messages coming in that SQL injection rules will actually look at and go, well, that looks like a SQL injection attack. That stuff should be allowed. You've got bot protection rules, which are in preview, and you've got geomatch filtering, which, depending on your region that you've deployed into, it's in preview or not. So you can start blocking certain countries from accessing your code. And this WAF, as I said, can be deployed on the front door. So it runs in every Azure region and the edge data centers. Or you can run it on the gateway, so it runs at a central point on a virtual network. And we've talked about that as well. How do we redirect traffic to our WAF? Well, it comes down to name resolution. If I'm publishing a web service through my WAF, that WAF has an IP address. So I can have my name configured to point at the front end IP of that WAF. And if it happens to be an internal WAF for private traffic across the site-to-site VPN, I can have a user-defined route that says, hey, anything going to my WAF just goes to virtual network, as you can see on the bottom left there. And then anything else that happens to be going directly to my spokes, well, there'll be a user-defined route to forward that through the firewall. There's a bunch of things that we can talk about, and I can see where we're running short on time. So service endpoints, and you're going to skip right quickly through to here. Service endpoints can be enabled on a subnet to give us a direct, more secure, lower latency path to service types. So not instances of services, but service types. So if I have an app service that I want to communicate with Azure SQL or Azure Storage accounts, I can say turn on the service endpoints for Azure SQL and Azure Storage, either globally or in this region. And now those paths, instead of going via internet, which is the public Azure backbone, those paths will now fall through a trapdoor and go straight to that resource type. So there's the networks in Azure that host those services. We have resource access policies, and these are firewall rules or access rules that we can run on our platform services. So on Azure SQL, I can enable a firewall rule that says only allow client connections from these particular addresses, whether they're fixed IP addresses or CIDR blocks. So now anyone who's trying to connect as an admin or anyone who's trying to run a query or an application against my database must be in those source locations. And you'll very often see this being used with service endpoints. You have the other type, which you'll see on the services like app services, where we can create access rules. Now, these aren't hard firewall rules that prevent the actual TCP connection, but what they are is a service denial. So I can connect to the web server, but I will be denied access to the web content. So we can use that as well. And these are still relevant, and they do play a role with service endpoints. And a new feature we're about to talk about here, which is private link and private endpoints. So one of the challenges about the platform is it's just naturally native public. We have these services, whether it's data lakes or Azure SQL, Cosmos DB. You think of a platform service. When you create it, it is naturally something that's on the internet. And most organizations don't like that. They want that to be private. Now, it causes challenges for developers, but we need to make it private. So we have a bunch of ways of dealing with that, lots and lots of them. But the newest one is private link. So private link is a service in the fabric that allows a type of resource like Azure SQL or storage account to surface itself using a private endpoint. And private link is a generally available service. Private endpoint is mixed levels of availability at this point, depending on the resource type. So Azure SQL and storage now support this. And this is where my service, my instance of a service, so my actual database server, my actual storage account can have an IP address on my VNet. And now combined with those firewall rules or access rules on the resource, I can start denying every other connection. You must come through that IP address on my VNet. So now I can start making platform resources private, not just public. So right now, this doesn't support inbound rules and SG rules. So that's why I talked about the firewall rules on the resource, or the access rules on the resource. but it does support outbound NSG rules, which is a bit wonky. But when you understand how it private link actually works, it makes sense. It's actually a close relative to service endpoint. You implemented your security, great. Now you need to monitor it. So there's already been sessions earlier today about Security Center. So you need to basically use Security Center. You can use the free tier to do your configuration. Do bear in mind, some of the recommendations are based on non-best practices that came out of a different product group, not Azure networking. And don't use it as Bible, use it as a checklist. This is not Microsoft telling you what's right to do and wrong to do. These are things that you should check. So do be wary of that. Take advantage of things like log analytics. You send your NSG data there, send your firewall data there. It is incredibly useful for troubleshooting application behavior in a microsegmented network. Paul earlier talked about Azure Sentinel in the previous session. Fantastic solution. Out of the box, it's not going to do an awful lot. It does require work, and have a look at Paul's session from earlier. I believe the sessions are recorded. He's an expert on this stuff. He's like one of the first people to really bring this into production usage with large clients. And again, log analytics. If you're doing any troubleshooting, it's log analytics. And as I said earlier, if there's anything wrong in your secure network, it is routing. It's not configured right. There's something you forgot to set up or you over-configured. And all these together give you your microsegmentation. This is something we've always known that should have been done, but it was too hard to do in the physical network. Now that we're dealing with software-defined services and things that we can deploy using infrastructure as code, these are things that we can implement and manage actually quite easily. So take advantage of some of the stuff that my colleague Damien is talking about right now, and be able to deploy this and manage it and maintain it on an ongoing basis, and use your log analytics to understand how it's behaving and where problems may reside. And you can start locking things down, so if you do get hit by the next WannaCry, it's not able to spread across your entire network. It's basically contained. And you can do that with your traditional VM stuff, and you can do that with your services as well.
Hey,
so literally wrapping up.
Yeah.
So that's
Thank
it.
you.
Thanks very much for tuning in, everyone.
Thank you. Aidan, do you want to just quickly, because we don't have time for questions, do you want to just quickly let people know where they can contact you?
Yeah, you can get me at Joe_Elway on Twitter, and find my blog on aidanfinn.com.
Awesome. Thank you so much. If you have any questions for Aidan, please go and hit him up on Twitter. We need to move on to our next session. So next up, we have Anita Ramanan, and I've made her a presenter, so we should be able to swap over. Anita's going to talk to us about quantum computing. She's a senior quantum software engineer working in the Microsoft Quantum Computing product group. Welcome, Anita.
Hello, can you see me and hear me?
Yes, we can see you.
Excellent. Let me just...
And I see a World of Warcraft icon. Awesome, love it.
Of course. Right, you can see the slides, everything ready?
Yep, we can see
Excellent.
the slides. Yep, we can see it all. So I'll just let you kick off because we're on the hour.
Great.
Cool.
All right, well, thank you very much for the introduction. As I'm Anita, I work in the quantum computing product group as a quantum software engineer, which is an interesting title. My background is kind of half and half physics and software engineering. I did physics in university, but then joined Microsoft as a grad and have been kind of developer consulting and then software engineering ever since. So I've been at Microsoft for about 5 years now. No, nearly 6. But anyway, today I wanted to kind of talk to you about quantum computing. So I'm going to tackle this from a kind of super high level beginner perspective, assuming no kind of knowledge. And if this kind of tickles your interest, I'll provide you with some links and things at the end. And also I'll be doing a webinar on the 7th of May, in which I'll walk through something called Grover's algorithm for searching unsorted databases more efficiently in quantum code in our Q# language. So that's a bit deeper level, but I'll get onto that later. So first things first. Before I kind of go on to explain what a quantum computer is, I wanted to give some reasons why we might want to actually build one in the first place, to kind of motivate us to why would this be a useful thing to do. So at Microsoft, we are focused mainly on these kind of 4 areas of quantum computing. Of course, we have research going on kind of across the spectrum, but these are the kind of 4 key pillars which we're currently pursuing. The first one is simulation. So I'll go into a bit more detail on this in a second, but this effectively means using a quantum computer to simulate a quantum entity, like a molecule or something like that, to a higher level of precision than we would be able to with a classical machine. Now, this isn't necessarily true for everything. We expect there to be advantages to using a quantum computer when you're trying to simulate particular molecules with atoms that come from the transition metals, for example, or the lanthanides and actinides, because the electrons in these elements are quite close together relative to the rest of the periodic table, and therefore the interactions between them become ignorable effectively. And trying to actually model what all of those electrons are doing, as well as relative to every other electron and the whole kind of configuration of that molecule, is something that is, as you might imagine, very, very difficult to do, and it's just not something where we have the capacity to do with a classical machine. So that kind of thing, that's what I mean when I say simulation. Cybersecurity. Now, one of the most famous uses for a quantum computer that I'm sure you've heard about is using it to break cryptography, right? So Rsa cryptography, it's largely dependent on the fact that factorizing a really big number is hard for a classical machine. And the idea is that it's theoretically, it'll take your hacker longer to break that to factorize that long number and get the and thus decrypt your data, then your secret would actually be valuable for, because it would take billions of years for an RSA like 2048 key or whatever to be kind of cracked by this kind of brute force attack. Problem is that quantum computers are exponentially more efficient at finding these kinds of prime factors, for example. And a key that might take 100 billion years, or sorry, 1 billion years on a classical machine would actually take something in the region of 100 seconds on a quantum machine, which is a little bit scary. Fortunately for us, there are both classical ways in which we can protect our data more effectively and make this resilient to quantum attack. So these are called post-quantum cryptography solutions. If you're curious about that, if you search for Microsoft post-quantum cryptography, we have a full page kind of dedicated to our efforts in that space. But the National Institute for Standards and Technology has put out a call for papers for new classical ways of encrypting data that aren't reliable on things that a quantum machine would be able to more easily crack. So that's one way. The other way is, of course, using a quantum computer to help us encrypt our data. So, for example, by exchanging cryptographic keys using a quantum protocol like quantum key distribution, we ensure that if someone actually intercepts that message and tries to read our key due to something called quantum no cloning theorem, which means that you cannot copy a stream of quantum information, or you cannot copy any quantum information. We will always know someone has intercepted that key. And that means that if we notice these errors appearing in our key, we can discard it and use a different channel for communication. So that's a different way in which we can kind of tackle the cybersecurity problem. Optimization. So this is actually what I do mostly for my job. So I kind of focus on something called quantum-inspired optimization methods, which take quantum optimization methods and dequantize them, by which I mean, so at the core of a quantum optimization method, there's usually some form of random walk. I'll go into this in more detail later. But what we do is we take that quantum random walk and we replace it with a classical random walk, and we can then run that on a classical machine. So we're actually seeing quite a lot of success using these optimization methods to tackle, highly complex, high-dimensional problems where machine learning, for example, can get easily stuck in a local optimum. For example, we're looking for these kind of really rugged optimization surfaces. Machine learning. I mean, when anyone jams three words like quantum machine learning together, there's going to be investment and interest. It's actually a relatively new area of research in terms of kind of quantum computing, as maybe 5-10 years old at max. But there's some interesting kind of areas that are, kind of showing some promise. Now, the main problem with something like quantum machine learning is that quantum computers do not work well with big data. The reason for that is that in order to transform our classically stored big data into some format that the quantum computer can actually read is really, really inefficient. So even if you had an exponentially more efficient way to solve a machine learning problem using a quantum machine, the time it would take to actually transform the classical information to quantum and then back out again at the end would usually negate that speed up. There are, however, problems where we can, for example, do smaller parts of that machine learning algorithm on a quantum machine to speed it up. So, for example, using this Grover's search algorithm, which I was talking about earlier, this allows us to take an unsorted database and find an element within it with root n complexity versus order of n complexity, which is classical, so you get a quadratic speed up. So we can kind of take these smaller chunks of machine learning algorithms and speed them up using a quantum machine, but not necessarily potentially taking a whole bunch of big data and putting it through a quantum machine learning algorithm. I'm not an expert in this field though, so but it's definitely an interesting one to look into if you're curious. I wanted to dive a little bit deeper into the kind of simulation part of this, because this is probably one of the earlier types of application that we'll see. So I wanted to kind of tell you a quick story about nitrogenase. So farming. So our population, back in the day, let me start this story again, sorry. In order to feed ourselves, we need to grow plants. Plants either feed livestock or feed ourselves directly, but the point being that we need to eat. Back in the day, it was relatively kind of straightforward to feed the world's population because there just weren't that many humans. Fields needed to get to be enriched with nitrogen so that the plants can build amino acids and proteins, and then we take those in. And that nitrogen usually came from decomposing organic matter, dead leaves, dead plants, cow manure, all this kind of a thing. Now, as the population of the world kind of started increasing, we ran out of the capability to actually fertilize enough fields to produce food to feed that kind of level of population. Fortunately for us, back in the 1900s, a couple of scientists called Haber and Bosch came up with a way of taking atmospheric nitrogen. This is kind of a triple bonded 2 nitrogen atoms glued together. And they invented a way called the Haber-Bosch process, which runs that over a hot catalyst at high pressure. So we're talking about 400 degrees Celsius and 200 atmospheres of pressure. And you combine these nitrogen molecules with hydrogen and you produce ammonia. And using that ammonia, we can produce fertilizer, which is great. And thus was enabled the expansion of the human population as we know it today. Now, as you might imagine, that is not a particularly energy efficient process. Actually, the process just of producing ammonia to fertilize our fields, our food supply, actually takes up something between, I think it's 1 or 2% of the global energy produced every single year, which is a little bit alarming when you think about it. I mean, you know, if there was a more efficient way in which we could do this, we could save an awful lot of carbon emissions. We could start tackling things like climate change, hopefully, and you know, it could have a pretty significant impact. So is there a more efficient way of doing this? As it turns out, yes. So back in the day, again, before this kind of Haber-Bosch process came along, farmers used to rotate beans into a field because, and beans would re-enrich the soil with nitrogen. And the reason for that is that in the roots of these beans, there are these nodules, and in these nodules live bacteria. And these bacteria use an enzyme called nitrogenase, which is kind of shown on the screen now. Now, nitrogenase, right in the middle there, has an active site. And it can take nitrogen in its triple bonded, super kind of strongly bonded form, and at room temperature and pressure, break that bond and combine each of the nitrogen atoms with hydrogen to produce ammonia. Fabulous. Why aren't we just manufacturing tons of this nitrogenase stuff and using that into this Haber-Bosch process? The problem is that the modeling of that active site, the thing that kind of actually does this magical breaking up and recombining process, we're not able to simulate it with enough accuracy to actually manufacture it efficiently or effectively, sorry, without just growing the beans. To give you an idea of how complicated it would be to actually accurately simulate that, this is the amount of memory that you would need to store all of the different configurations of that active site, which contains some iron and some molybdenum atoms, which is why that's what I was talking about with the electrons. Their motions are correlated, and it makes it very difficult for us to simulate. Now, to put that into perspective, that 1.5 times 10 to the 51 bits of RAM would be the equivalent of 10 Earth-sized planets, where every single atom is being used as RAM for this simulation, which is clearly not going to happen. Alternatively, we could use 170 logical qubits. Now, bear in mind, a qubit is something like an atom or a molecule or something on a quantum scale. That suddenly seems a hell of a lot more achievable. Now, one caveat to this is when I say 170 qubits, I mean 170 logical qubits. That means, one logical qubit is a fully error-corrected qubit. Now, that might actually consist of anywhere between 10 and 1,000 or 10,000 physical qubits, because qubits are very error-prone. They're prone to they lose their quantum states when they interact with the environment. So we have to have extra qubits around physically to detect and correct these errors as the calculations kind of go on. But still, this is a much more achievable number than 10 Earth-sized planets where all the atoms are acting as memory for us. So we've had the preamble, why we would want to build a quantum computer. Why would a quantum computer be any better than a classical machine at any of this? Ultimately, it comes down to a few kind of quantum phenomena, one of the most significant of which is called superposition. So on the left-hand side here, we have two light bulbs. One is off and one is on. These are kind of representing our classical bit, right? So it can either be 0 or it can be 1. And that's pretty much it. This was what drives all of our modern calculations and my World of Warcraft and everything else that we kind of use on a daily basis. A quantum bit, on the other hand, you can kind of think a bit more of like this dimmer switch on the right-hand side. It can exist in a purely 0 or a purely 1 state, but it can also exist in something called a superposition, which is usually where you'd hear someone say this kind of, it can be 0 or 1 and 1 at the same time. But more realistically, it can exist in a probabilistic kind of, let's say, cloud. And we can do calculations when it's in this superposition, in this kind of probabilistic state. But when we take a measurement of that state, it will collapse either to 0 or 1. So we always end up with binary information out. But whilst it's in that superposition, that's where the magic happens, right? Because that's something that you just physically cannot do with a classical bit. How does that manifest itself? So I've mentioned Grover's algorithm a couple of times. Here's a kind of visual representation of how that kind of works classically, right? So we have this maze. What we have a kind of database, if you can imagine, of all of these different routes. And what we want to do is find the route that leads us to the center of the maze. Now, classically, because it's unsorted database, there's no order to it, we're just doomed to try and keep trying different routes up until we find the answer, which is not particularly efficient and scales as the size of the database scales linearly. In a quantum scenario, so let's imagine now this is a quantum database. We're ignoring the problem of translating the data into the quantum format for now. What we do is we put all of the elements in this database into this superposition state. So now we can see all of these routes. So each route representing an item in the database of solutions. And then what we can do is we can interfere these states with one another. We can set the problem up in such a way that the route that we're looking for constructively interferes with itself, and every single other route destructively interferes. We do this a few times. As you can see, I mean, the kind of thickness of these lines is representing the probability amplitude. This is, you know, when we take a measurement, we're now very likely to see the thickest line come out, the one with the highest probability amplitude. And we're very unlikely to see any of these ones with the thin lines. Of course, it's still a probabilistic science. You'll still have to redo this experiment a few times in order to kind of confirm that this is the answer that you're looking for. But that very quickly converges. And as I say, this is a quadratic speed up over the best classical case. Okay, so we have superposition. There's a number of other phenomena, but that kind of make these quantum computers special. But we'll focus on the superposition for now. How on earth do we build a machine that uses these principles? Like, how does this work physically? There are a few principles. These are David DiVincenzo, I think it was in 1995, came up with these kind of 5 principles that, 5 criteria that we can use to judge how useful a quantum computer is, or if we can in fact call something a quantum computer. These, I'll kind of quickly run through them. Easy reset just means that we need to be able to reliably and easily reset our system into a nice, simple starting state, same as any other classical machine. So let's say all of our qubits in the system are in state 0. That's our nice kind of starting state from which we can then do our kind of quantum computation. These qubits need to be measurable, right? Ultimately, if we have no way of looking inside the box and figuring out what's happened, it's kind of useless to us. So even if you've got the best error-free solution in the world, if you can't measure it, you might as well not bother. So that's a fairly straightforward one. It must be universal. This means that we need to be able to, from a kind of a simple small set of single and double qubit gates, like NOT and controlled NOT and swap and things like that, we need to be able to construct any more complicated circuit that we might want to actually perform on this machine. Now, there's a few known kind of universal sets of gates. And as long as a quantum system can actually construct all of those gates physically, then it can be called universal and we're good to go. Now, I specifically kind of left scalable and stable till last. The reason for that is that these are the 2 real killers right now. Scaling these systems is really difficult because our technology needs to evolve further, that we need to be able to, get enough qubits of high enough quality onto a chip and be able to control those qubits with well enough at temperatures that are millikelvin above absolute zero, which is minus 273 degrees-ish Celsius. That engineering challenge is insane in and of itself. And the other problem is we need to be able to keep these qubits in their nice known quantum states, these superpositions, for long enough to actually do our calculations, do our computation, right? So, I mean, if your operation takes 10 seconds, but the lifetime of your qubit before it decays into just a kind of random bit, it's only 5 seconds, then you're kind of screwed. But if it's the other way around, you've got some space to work with. So these scalability and stability requirements are really what's preventing us from having these machines available at scale today. You'll hear a lot about, kind of companies like IBM and Google and Rigetti and a whole bunch of other vendors out there. They're making great progress, but they have systems which are about 100-ish qubits max. And they're noisy. They're not 100 logical qubits, they're just 100 physical ones. And the amount of error correction that we need to do there is at the minute, it's holding us back from being able to build larger systems. Because if you need, say, 1,000 qubits per single logical qubit, as you add more qubits, you can see how this might become a kind of scalability problem. So these are known as noisy intermediate scale quantum devices. And these are kind of the ones that you hear about in the news today. This is where we're kind of at. One example, oh, I've lost some slides. One example of a NISQ device, a noisy intermediate scale quantum device, is called an ion trap quantum computer. So what we do is we take ions, which are just charged particles. They've gained or lost electrons. And we can hold them in a trap using magnetic and electric fields. So they're pretty, they're easy to move around. They're easy to reset. They're pretty easy to manufacture. Like salt is made of ions. They're pretty common. And the way that we form a two-state system, so our zeros and our ones, is that we can excite this ion by shooting lasers at it. So you shoot a photon of light from the laser, and that excites the ion from a lower energy state to a higher energy state, and that's our 0 to 1 transition. And then it can go back down from 1 to 0 by emitting a photon, which we can measure, and going from this higher energy state to the lower energy state, which gives us our 1 to 0 transition. So that's a kind of an example of a two-state system. Ion trap quantum computers are actually they're one of the more relatively stable systems that we have today, but they're still not stable enough for us to really build them at scale yet. So ion trap is one example of a NISQ device. You also have superconducting qubits, molecular kind of qubits, photonic qubits using light particles. There's a kind of a wide variety of them available out there. In fact, I think if you're curious about the hardware side of things, I'd recommend there's a Wikipedia page on quantum computing hardware, and it gives a good kind of list of the various different types of devices, which is a good kind of starting point if you're curious to learn more. At Microsoft, we decided that instead of, we're also manufacturing quantum computing hardware. But instead of trying to manufacture these NISQ devices, we decided to take a slightly different tack. So we're trying to build a quantum computer using something called a Majorana Fermion. Now, a Majorana Fermion is a two-dimensional anion. It's a kind of quasi-particle. It's really weird, but you can kind of think of it. So we get these nanowires they're superconducting nanowires. And you might have seen these pictures of these giant kind of brass chandelier things hanging from the ceiling. So that's called a dilution refrigerator. So that's what kind of takes us from room temperature at the top through liquid nitrogen at 77 Kelvin, through liquid helium at 4 Kelvin, and then it cycles 2 phases of liquid helium at the very bottom of this kind of tower to bring us all the way down to 15 millikelvin, which is pretty much the coldest place in the universe, which is pretty cool. But at the very bottom of these sits our quantum chip. And the one that we're trying to build, it consists of these nanowires. And when you cool them down to these super low temperatures, the electrons start to behave weirdly. So they start to form these chains. And there's a kind of half electron cap at each end of the chain. Now, if we brought the two ends of the chain together, the half electrons will either annihilate to form no electron, that's our 0 state, or they'll combine to form an electron, which is our 1 state. But the idea is that because they're separated by the electrons in the middle of that chain, they're topologically protected. And that means that they're much less susceptible to noise, to interference, to cosmic rays that you just can't shield from, or fluctuations in temperature because you can't ever get anything to actually absolute 0. It means they're much more susceptible to these kinds of changes. So we do quantum operations on them by braiding them, by actually kind of tying these knots. So that's what this picture is trying to show you. So if you imagine time being along the vertical axis, and we've got like these 6 qubits in our wire, and we braid them. And as time goes on, they interact with the environment a little bit, and they kind of the strings are less neatly aligned on the right hand side, but the braid pattern, the actual quantum information, is maintained. So this is the kind of this should be an inherently less error prone, like orders of magnitude less error prone quantum computer than a lot of the NIST devices that are out there today. It is unfortunately new science. We need to invent new physics. We need to invent new engineering. We have a whole lab in Sydney focused on cryocomputing, on how do we control these weird qubits, and labs across Europe in Delft and Copenhagen focused around actually building them. So it's earlier. It's not commercially available these days or yet, but watch this space. If we can pull it off, it should propel us into an interesting future with much less error-prone quantum computers. Now, I've spoken kind of about hardware. We also have a quantum development kit software. This is comprised of a set of libraries, which they allow you to do lots of basic operations in the same way as a library in C# or whatever language is your preference works. We've kind of tried to move the bar for quantum computing away from literally assembling circuits to at least being able to access some kind of higher level software engineering kind of style tools. Hence our libraries. There's a chemistry library, there's a numerics library. There's actually more recently a machine learning library that we've introduced. Then you have the core language, Q#, domain-specific language for building these quantum algorithms. And this kind of works alongside a classical program. So you can kind of think of it like a machine learning application, where you have the classical code, doing the kind of basic I/O and the data visualization and all that kind of a thing. And then you call a GPU when you really need that speed up, when it can actually provide you with some advantage. Because whilst you technically could write everything and run it on a GPU, it'd be a pain and it would be really expensive. CPUs, classical machines, are pretty good at a lot of things. A quantum machine is not going to magically replace all of our classical machines. It's not going to be better at everything. Just because you can do something on a quantum computer doesn't mean it necessarily will be more efficient than on a classical machine. But in those instances where it does have an advantage, this is where we can kind of leverage it. So you have this kind of classical host written in, let's say, C# or Python or anything that supports .NET really. And then you have your Q# program, and you kind of use these as kind of co-processors, right? So you run most of the stuff on CPU and then call your quantum machine when it's going to help. So for the time being, obviously, there's no commercial scale quantum hardware available. But what we do have is a kind of variety of different types of simulators. So we have a quantum simulator that simulates the full state of a quantum system. So this is limited in scale because every single time you add a qubit, you double the amount of memory that you need to actually simulate the system and all its interactions. So if you have about 16 gigs of RAM, you can simulate about 30 qubits on a good day. If you have 16 terabytes, you can get up to about 40. And then the maximum number that you can really do today on a classical machine is about 50 qubits, because you're hitting 16 petabytes of RAM at that point, and that is basically the size of the biggest supercomputers we have available to us today. So realistically, we're never going to be able to simulate enough qubits to do anything particularly helpful on a classical machine. However, we have other types of simulator. So we have resource estimators. So our chemists, our research teams are actually currently using this resource estimator to help them to design and optimize their quantum algorithms, so that when hardware becomes available, we're able to run these algorithms on the smallest set possible and the lowest number of qubits, because we've written and tested and optimized these algorithms using the things like the resource estimator. And there's a few other different types, but I'll share a link at the end, which you can kind of go to explore all of this in more detail. Of course, when hardware does become available, we don't want to have to rewrite all of our code. Fortunately for us, that's actually a one-line code change in Q#. All you need to do is change your target, and provided that someone's written a compiler for that particular quantum hardware for Q#, you're good to go. You can just switch and run. And this is kind of where Azure Quantum comes in. So this brings together our hardware efforts, our kind of our qubits, but also we're partnering with people like Honeywell, who manufacture ion trap qubits, IonQ, who do the same, and QCI, who manufacture superconducting qubits. And these will all be available through the Azure Quantum interface, in the same way as you can target a different type of hardware today using a classical machine. We, of course, I've just gone through the quantum software, so that includes the Q#, simulators, resource estimators, and then so Azure Quantum is in private preview right now, but keep your eyes peeled around build time. Hopefully there'll be some announcements. Actually, I forgot to mention the Quantum Development Kit is available for Mac, for PC, available on Linux. It's all open source. You can absolutely go and check it out on GitHub, mess around with the compiler, the simulator code, the Q# language code. It's all there. Please do come and join the community. And Azure Quantum also contains these quantum solutions. So these are these quantum-inspired optimizer methods that I was talking about earlier. So these provide you a way in which you can, submit problems to the quantum-inspired optimization solvers and get answers, depending on the type of problem you have, more efficiently than you otherwise could on a classical machine. This slide should have been before the other one. Apologies for that. But this is just effectively running through what I was saying about Q#. So we can see this kind of co-processor architecture where we have the quantum code and then the classical host. And then these are the two runtimes, so simulator based right now and the cryo control and quantum computer in the future. So with that, I'd like to change tack a little bit. I've kind of covered off, the basics of what a quantum computer is, why we might want to build one, and how we would go about building one. And now I'd like to cover off something that is more applicable today. So firstly, a little disambiguation. So when I say quantum-inspired algorithms, these are purely classical. They're running on classical hardware. They're written using classical code, C++, C, that kind of a thing, Python to prototype. But we can run these today. We prototype on CPU, and then we accelerate using GPU or FPGA in Azure. And we surface these either through a custom work stream, a custom project with a customer, or through the Azure Quantum solvers, which will be available once it hits private preview, and then obviously as the system kind of becomes more widely available. Now these contrast with these kind of actual native universal quantum algorithms, which run on real quantum hardware, which this is what you would use Q# to write in conjunction with C# or Python or whatever it is you're using for your classical driver. But this quantum hardware is realistically probably, don't quote me on this, but about 5 to 10 years realistically for commercially available scaled quantum computing, error corrected. That's going to be at any scale that's useful for us to actually do new things with. Doesn't mean we shouldn't be investing now. We should absolutely be learning how to code for these machines. We should be writing algorithms today in order to target these machines as soon as we possibly can. But in the meantime, we can apply quantum-inspired optimization, which we can run just classically today. So what do I actually mean by QIO? So let's imagine we have this problem. This is obviously highly simplified, but we have some sort of cost that we're trying to minimize up the y-axis, and we have a configuration of variables along the x-axis. So this is any combination of, say, we're trying to route trucks around a city and they're delivering things. So, it'd be the cost of having an extra truck on the road, or the hourly cost of driving said truck around, or picking up and dropping off different packages optimally, this kind of traveling salesman problem. Now, traditionally, if you have a problem that's really rugged, there's lots of these kind of local optima, it's very easy to get stuck in something that's not this global optimum. And this is something that machine learning struggles with sometimes, depending on the kind of particular optimization landscape. The reason for that is that this jump, what a physicist would call a thermal jump, if you're kind of assuming this is an energy landscape, it's hard to overcome. I mean, you can use something like momentum, but if that's a very, very tall barrier, it's going to be very unlikely that your system is going to be able to cross it. Now, this is where physics comes in. So in physics, there's a phenomenon called quantum tunneling that basically gives us an exponentially decaying probability that if you have a tall but thin barrier, it can be infinitely tall, or it can be very, very tall. I'm not sure it can be infinitely tall, can't remember. There's a finite probability that the quantum particle can cease to exist on this side of the wall and spontaneously exist on the other side. And what we do in as part of some of the QIO methods that we implement is emulate that effectively. We say, well, quantum tunneling is an efficient direct hop, but the QIO method emulates that to a level that's efficient enough to give us speed up in certain types, with certain types of problems, in comparison to a purely classical method. Obviously, this is an oversimplification, and there's lots of different types of quantum-inspired optimization algorithms which leverage different types of quantum principles. But one of the key ideas here is tunneling. So what we're looking for a problem that is to be tackled with QAO is something that kind of we see on the right. This really rugged. There's loads of different local optima that we can easily get stuck in. Something that with a very large search space, lots of variables to combine, parameters to optimize. Something that a machine learning algorithm would take a very long time to solve well. On the left-hand side, of course, I mean, we could write a QIO algorithm to tackle that problem, but it's super convex, and you'd be better off just using a gradient descent. It would be cheaper and easier, and you'd get there faster. So to give you a flavor of the types of problems that we're actually applying these methods to today, The first case study that I wanted to talk about was Case Western Reserve University. So this is a university that's tied to the Cleveland Clinic in Ohio, sorry. And they've invented this method of doing MRI scans called magnetic resonance fingerprinting that massively speeds up taking an MRI. So basically, a traditional MRI, you can only really scan for one tissue type at a time using a specific magnetic set of magnetic pulses. Whereas these fingerprinting methods use a kind of continuously varying sequence of pulses and notes the response and matches the response against a big library of different tissue types, the fingerprints. And this enables them to cut down the amount of time it takes to do an MRI quite significantly, and actually to get more kind of robust and quantitative results. Now, unfortunately, designing these pulse sequences and getting them so that they're really optimal and they take as little time as possible is a really complex problem, and it's something that they were unable to solve using their classical solvers. So we got involved. We said, okay, so can we apply QIO here to help you optimize these pulse sequences? So this is what the pipeline for that looks like. So we have a QIO method. This is all sitting in Azure. It generates a proposed pulse sequence. That's run against an MRI simulator in Azure, which runs the MRI using that particular pulse against a simulated human head, in this case, and then measures those results against a couple of different quality metrics. And if the pulse sequence doesn't pass, then it gets fed back into the QIO method, and you get this kind of feedback loop. Now, at the point that those quality metrics are passed, those optimized pulse sequences are then applied on a real machine to real people. So largely med students at the university, but also volunteer who had a brain tumor, for example, has been tested. And that's kind of the stage that we're at now. We're currently kind of in the process of getting these pulse sequences FDA approved, and the idea is that eventually these pulse sequences will be shipped out. It's just a software update to the existing scanners. They don't need any specialist hardware. So we applied these QIO methods, and these are scans. So on the left-hand side, this is the current state of the art. So these are the best pulse sequences that the team at Case Western could come up with using their vast knowledge of radiology and of MRI technology and all of that. And on the right-hand side is the ones are the images produced from a QIO generated pulse sequence. Now, to a radiologist, those are basically indistinguishable. And actually, it turns out that quantitatively, the QIO generated ones actually have a lower error rate, a higher precision. Most importantly, though, the QIO generated pulse sequence, that scan takes a third of the time than the current state of the art scan takes. Now, bear in mind this 35 seconds and 11 seconds that are quoted at the bottom of the screen are actually the time taken to do a single slice. This, an MRI for your head can take, anything up to say 90 minutes or so. If we can chop that time to 30 minutes, it opens up, you can get suddenly 3 times more patients through. You can reduce waiting times massively. You don't necessarily have to sedate children to keep them still for long enough, or people who are highly claustrophobic. And these are kind of early results, actually. I think there's some slightly better numbers that we've kind of done since that. More interestingly as well, so at the bottom we see the QIO generated pulse sequences, and at the top we see the ones generated by the human experts. And as you can see, these are vastly different, particularly the ones on the right-hand side. And this has actually triggered a kind of another feedback loop to the researchers or the research team at the university, say, well, why should it be that these particular pulse sequences that look so far removed from everything our human intuition should give us, or it says should produce a good scan, why are these producing better results in less time? And this is actually then now prompting new research into it. So we've kind of got this interesting feedback loop from between the QIO generation of the pulse sequences and the actual research team at the university. Starting to run out of time, so really quickly I'll go through one last example. So the pulse sequences were an example of continuous variable optimization. This is a traffic optimization case study. So this is the one I worked on. What we did was we took 5,000 cars all traveling around Seattle and Redmond at rush hour, and they were trying to get to the airport, which is kind of south of Seattle city itself. So we took these 5,000 cars. It's Friday, it's rush hour. We give them 10 options each for the route. And we say minimize the congestion across the whole system, but also don't increase the amount of time it takes for people to actually get to the destination, because ultimately, yes, you could increase congestion by sending someone on a 3-hour detour, but no one's going to want to do that. So it's going to be kind of a pointless solution. So this is what it looks like. On the right-hand side, we see the simulation running. So it took us on I think it was a Surface Book, kind of standard laptop machine running. It took it 26 seconds to do this optimization. And we saw a reduction in the congestion level of 73% and a reduction in the average commute time for each kind of car in that simulation of 8%. Now, this is obviously a balancing act. We could focus more on the minimization of the commute time versus the congestion level. But the idea is that, even using very kind of basic hardware, we can see some significant results, which could potentially be used to, reduce, improve air quality, for example, or used for designing of city centers to minimize congestion kind of more intelligently. These, of course, aren't the only scenarios that we're looking to kind of tackle. The routing and logistics that I just showed you, that example was work we did with Ford. There's lots of different kind of logistics problems, traveling salesman problems, capacitated vehicle routing that we're looking at. Power grid management, so we're working with the Dubai Electricity and Water Authority to help them optimize the way they generate electricity. So they co-generate electricity and water, which is a really interesting problem. So you have to make sure that you have the minimum set of equipment turned on at any one time to generate the enough to satisfy demand plus a margin in case there's a massive surge. So that's kind of quite complicated optimization problem. Then there's, of course, things like material discovery, process optimization, this traffic routing thing, kind of in an emergency scenario, how do you route ambulances most effectively around, or, emergency vehicles. And then finance. So we're working with Willis Towers Watson, we're a big risk management firm in the UK, to help them to optimize the way that they model risk. So we're seeing some success with that. These slides will be, I think, available afterwards, so you can kind of click on the links and explore those case studies if you're curious. So for next steps, if you're interested in learning more about Azure Quantum and signing up for the private or public preview, when it is available, check out that first link. Comprehensive documentation is available at our doc site, which is the second link. We've just gone through a lot of effort to revamp everything. It's got a lot of kind of 101 information on what quantum computing is, how you code for a quantum computer, all of this kind of information, including some kind of basic maths and kind of, complex maths tutorials and things. So definitely check that one out. The Quantum Development Kit is available at microsoft.com/quantum. So you can go there, you can download the QDK, which includes all the simulators and Q# and the libraries and everything you need to actually write a quantum application. And then the last two, so the first one is just a link to the main quantum GitHub page that contains all of the libraries, all the simulator, everything's open source, as I say. The last link is actually probably it's my favorite. It's the most useful one if you're trying to learn this. So particularly if you're coming from a software engineering background, the quantum katas are kind of a challenge-based way to learn everything, starting from the kind of maths behind quantum computing. It takes you through, kind of complex maths, It's all in a Jupyter notebook. So you write a little bit of code, run it. It runs a test, gives you a hint if you got it wrong. This kind of thing. It's really, really good way to get started with both Q# and quantum computing more generally. So I definitely recommend that one. And if this has got you interested in quantum computing and you're curious about learning more about Grover's algorithm specifically, as I said at the beginning, on the 7th of May, I'll be running a webinar where I'll be, well, the first half is kind of what I presented in the first half of this today, but the second half goes into a deep dive implementing Grover's algorithm in Q#, and kind of doing it step by step and explaining kind of quantum tricks. So some of that constructive and destructive interference I was talking about. And with that's all the content I have. I'd love to take your questions. I know we've only got 8 minutes, my bad. Yeah, thank you very much for joining. And feel free to reach out on Twitter. My Twitter tag is there. So.
Thank you, Anita. So I invite everyone in the meanwhile to drop any questions on the chat in case you have any questions. I have actually one question here for you. So, do you see a future where everyone would develop on a quantum computer?
No, so I don't think that classical computers are going away. As I say, they're very good at doing a lot of things. We've optimized them pretty well to do the majority of things we're really going to need. It's the same kind of question as do you see a future in which we'd run everything on a GPU? Probably not. I mean, we could. A quantum computer is a kind of superset of a classical computer. You can do everything a classical computer could on a quantum machine. But just because you can doesn't mean you should, I guess. So no, classical machines aren't going away anytime soon.
And you shared some links there where people could go to get started, but would you say that having a quantum physics background is essential for someone who doesn't have that background? How would you recommend that they get started?
So no, I mean, I would absolutely not. So for example, our team is pretty much 50-50 people, from quantum research backgrounds. I mean, I don't have a quantum research. I just did my kind of master's and then started doing software stuff at Microsoft. But the other half of the team are all software engineers, computer science backgrounds. And we're actively looking to hire more of these kind of people, from different diverse backgrounds, because if you have a team that entirely consists of researchers, you're only going to get one type of solution out, or kind of small subset of solutions out, because they all think in a fairly similar way. And we've actually found that by bringing more software engineers in, and machine learning people as well, we've really enriched the program and kind of driven it to be much more of a software engineering kind of friendly. Q# is really designed to be friendlier to a software engineer, computer scientist, than potentially some of the other frameworks available out there. So in terms of learning, if you are a software engineer and you're curious about how all this works, I have a very old blog with a friend, Frances, who also works. She's from a software engineering background, which I can post a link to. So that's kind of aimed at the kind of software engineering level, but it's quite out of date, so the Q# won't be up to date. But the katas that I linked, I think, are really the best place to go, and the documentation site. And yes, I saw there was a question about posting the links, and I will post those in the chat in a sec.
Awesome.
Right. I have another question for you, Anita, just to close up. Do you consider quantum as an essential skill for developers going forward?
I think that, kind of like machine learning, it's worth understanding, worth most people at least understanding what a quantum computer can be used for, and if whatever it is you're doing can be accelerated by a quantum computer. I think it's just a hugely interesting thing to learn about anyway. So I definitely encourage you to learn. But I think it's going to be more in the style of the kind of machine learning. Not everyone needs to be an ML expert. It's good to understand when it's applicable, so that you don't miss out on opportunities. But if everyone was a quantum expert, then we'd have no regular software engineers, and it'd be a bit of a nightmare in the other direction. So, yeah, no, I don't think it'd be completely essential, but a useful skill for sure.
Okay, so I would say maybe we can close out and move to the next section.
Sure. Yeah. I'll post the links in the chat now as well. And I'll send a PDF. Should I send it to you or post it in the chat?
You can post the PDFs and post the links in the chat if you want. Yeah, I think that would be a good idea. It might take us some time to get the videos edited and out there for the recorded sessions. So
Right.
yeah, that'd probably be a good idea.
I'll do that in the meantime. Fabulous. Well, it was great talking to all of you. Thank you very much for joining, and enjoy the rest of the bootcamp.
Thank you, Anita.
Thanks for joining us.
Thanks so much.
Bye.
So I would say, Lisa, before maybe we move to the next session, we'll share the agenda for the last sessions we have.
Yes, definitely. Go for it.
Okay, so let me know when you can see my screen.
Yep, I can see you.
Yeah. Okay, so as you know, we have still the 3 tracks live, and on the first track we have Power Automates Your Way to Cognitive Service and Power BI, provided by Ben. And also we have on track 2 using Azure DevOps for serverless PowerShell, delivered by Vukazin. Sorry if I spelled wrong. And on this track we have Azure Firewall Manager with the latest features provided by Onur. So I assume, Onur, are you ready? Yeah. Okay. Onur, are you there?
He is showing it here.
Yeah, and he unmuted just right now, but maybe there is some issue with
Yeah, maybe
sounds.
Maybe an audio issue.
Can you hear me now?
Yeah.
Okay. Yes.
Hello there. Sorry about that. Yeah.
Okay. No worries.
Yeah, I'm totally ready. Are we gonna wait for a couple of minutes for the others to trickle in, or are we good to go now?
Let's wait a minute or two until
Sure.
people will be swapping between streams and stuff.
Absolutely.
Yeah, so you can just test your presenting and that kind of stuff.
Okay. All right. Great.
In the meanwhile, we would be really happy to ask everyone to provide feedback about all the sessions, just to understand how good you think they are, or if there are any suggestions on how to improve it. You are more than welcome. Okay, we can see your screen now.
Yep.
Awesome. Okay.
Can you just
I'm going to get started in a minute then.
Yeah. Let's just.
Also, during the session, feel free to drop any questions in case you have questions. We will collect all the questions at the end, and we'll ask to the speaker.
Yep. Let me give you the link to track 1. I can do that.
Thank you, Elizabeth, for the feedback.
Yeah, that's great. I think people are still switching in and out. Okay.
And thank you, everyone, to stay with us. Okay, of course, it's important.
Yeah.
To acknowledge it. So, Onur, are you ready?
Yes, I am. Can I go?
Should we start with?
Let's just.
It's 4 o'clock, so sometime I would say. What do you think?
Yeah, I think we just kick off, and we might see some people joining in and out. Yeah.
Awesome. Thanks very much. Here we go then. Hi everyone. Welcome to my session today. First, thanks very much for joining us on this Saturday, and thanks for your patience throughout the day. Indeed, really appreciated your time and contribution. Okay, a little bit about myself before I kick it off. My name is Onur Okutucu. I live in London, and I'm running my own business here in London, and I'm basically a DevOps consultant, and doing a lot of automation as part of my work. And apart from that one, I'm also a Microsoft MVP for PowerShell since 2009 and still counting proudly. Yes, I've been trying to contribute to the technical communities as much as I can over the past 15 years. So I love that, really. So yeah, but I'd like to thank everybody, who has made a tremendous effort to make this wonderful series of events happen. So that's why it's just one of the biggest events around the world, right? It's just great to be a part of it once again. Thanks. Let's get started then. All right. First, let's have a look at our agenda today. And the first, I'm going to be talking about the new features of Azure Firewall that have arrived in recently. I know this is not, I mean, well, the reason that I put it in there is that I thought that'd be useful to cover the recent updates and the changes that came to the Azure Firewall. Well, despite today, we're going to focus on the Azure Firewall Manager instead of Azure Firewall for the rest of the presentation, but still wanted to give you a quick update of what's been changed so far, right? I don't see any harm in brushing up on it, to be honest. So I'll also give you a quick demo of what we have so far in terms of recent updates on Azure Firewall. And the next is that we're going to be looking at Azure Firewall Manager, of course, which is a brand new service to manage a lot of cool stuff in there. And once we looked at the Azure Firewall Manager principles and the fundamentals, we're going to be moving on to the architecture types for the next step, right? This is actually, where the things might seem to be a little bit confusing, but I'll try my best to just make it clear, right? Okay, and then the next is going to be the firewall policy versus firewall rules. Yeah, this is also one of the things that I thought I'd mention to show you the differences between the traditional Azure firewall rules and brand new firewall policies, because there are some significant differences between them, but sometimes it's kind of confusing. And then next, I'll have a look at the deployment scenarios and how we're going to deploy the things in Azure Firewall Manager, how to convert existing resources, and how we can make use of existing firewall rules, that side of things. And the last one before the demo will be like policy processing, and because there are different types of rules available on Azure Firewall right now. So on top of that, now we're gonna have some other rule collections that come with like inherited rule collections. So it will be like lots of rules for the firewalls to take care of, like in a certain order, I would say. So that's where we're gonna discuss all of this today. And the last, but not least, of course, and we'll finally be getting our hands dirty today. And then first, I'll walk you through the resources that that we're going to use along with Azure Firewall Manager, and then I'll show you how to configure policies and how to integrate virtual networks or secure hubs, and like how to manage a hub and spoke model in your environment. And then obviously we're going to have a quick Q&A session before I run away. Right. Okay. This first is Azure Firewall. Yeah. As you may know, this is a kind of standalone security service on Azure that we use in order to control all the network traffic using a set of rules. Of course, there are a bunch of different network or security services available on Azure, but this is kind of specifically Azure Firewall as a service kind of service on Azure. So Firewall, actually, the Azure Firewall has been around for like a couple of years already, and it's kind of service that we use on a virtual network, right? So simply what we need to do to control the traffic in a virtual network through Firewall is to configure subnets within a virtual network to work with Azure Firewall. Yeah, so that all traffic goes through Firewall, basically. This is a kind of traditional Azure Firewall approach that has been in use for so long. So that's the way that it works, actually. So on top of this architecture, recently there have been many cool updates that we've seen so far on Azure Firewall. That's why I just wanted to put it in there. So for example, now we are able to consume multiple public IP addresses, just like up to 100 IPs to be precise. So this is a very useful especially when you need to manage your environment more flexibly. It's like putting a lot of rule collections and they're being served through multiple IPs. Yeah, I mean, I think it will just make life a lot easier. So there are many other cool stuff came in, and for example, availability zones becoming a GA is a cool thing, which now provides us 99.99% availability. As far as I remember, it used to be like 99.95, but yeah, it makes a big difference, trust me. So it's just now, more available, I can say. And of course, a threat intelligence-based filtering is a kind of completely new thing, because when it was first rolled out, I mean, the Azure Firewall, we didn't have that stuff. So it's like a part of Firewall now, which is a big jump, I think. So threat intelligence-based filtering, it can just generate alerts and deny traffic towards malicious IP address and domains. But the actual thing behind the scene is a kind of like a more impressive, I think, because the IP addresses and the domains, I mean, the malicious IP addresses and domains are sourced from the Microsoft Threat Intelligence feed. So that's a kind of common service is used by multiple services, including Azure Security Center. So I'm pretty sure that would ring a bell because it's or like a huge service that is being shared by many other services. Okay, and the HT Insight is now one of those FQDN tags on Azure Firewall. As you guys may remember, there are some other useful FQDN tags, such as Windows Update, Azure Backup, or App Service Environments are also available on Firewall. So the HT Insight is the newest element of this tagging thing on Azure Firewall, so which is cool. I mean, the tags are just like a bunch of services and IP addresses that you can use on your Azure Firewall, so you don't have to remember the public IP addresses that may change all the time, right? So so that's a good thing. I'll also just give it a go and just give you a quick demo on that stuff as well. And what else? yeah, SQL filtering in preview, FQDN filtering in preview. That's a cool thing as well, because I take this as the kind of the first step of providing the ability to support all the ports and protocols on Azure Firewall. Unfortunately, it's not yet in place now, but that'd be great if it could. But thinking that it used to be like HTTP and HTTPS only. This is still something, but now it says that it does support Microsoft SQL protocol along with its port 1433, so which is really awesome. So now we can simply say that you can use the FQDN filtering for HTTP, HTTPS, and Microsoft SQL Server. And the last one here is the IP groups. I don't know if any of you have used this before, but this is also one of the preview features on Azure. But it's a cool resource on Azure, which we can use to identify a group of IP addresses, as its name implies. It's a kind of simple solution on Azure where you put all your IPs, IP ranges, or CIDR notations in advance, and then you can use them in Azure Firewall rules. So you don't have to just enter your IPs, IP ranges, or CIDR notations one by one for each of your Azure Firewall rules. So this is a kind of predefined set of IP addresses that you can use for all your workloads in terms of firewall rules across your organization. That's a good thing. All right. Let me just go to the portal and give you a quick demo around the firewall updates here. First of all, I'm going to show you the multiple public IPs. All right, at the first glance, you can see this is one of the latest developments on Azure Firewall, right? So threat intelligence. So pretty easy to configure. Actually, there are two options. The one is alert only, and the other one is alert and deny, right? This is by default, but you can just change it anytime you want. Click on the public IP configuration. You can see there are two IP addresses, public IP addresses here. So when I click on add a public IP configuration, just give it a name. You can see there is no public IP address available here. So because I have to create a public IP address in advance, I have to create it first, and then we just consume that public IP address out of this, and then we can consume this feature here. As I said, it's 100 public IP address supported here now. I think it's enough, right? I mean, it's kind of sufficient for now. Okay. There is one important thing to understand here is that the public IP address that you create in advance must be, I would say, a standard public IP address because there are simply two types of public IP address that you can create. One is basic and the other one is standard. If you want to use this functionality, you have to make sure that your public IP address that you want to create is standard public IP address. Otherwise, it won't just show up here, so you won't be able to pick that up from the box and use it. All right, and let me just go back to IP groups. Okay. Right. When I click on the rules, they're pretty much the same, but actually the things that I need to show you is just here, right? When I click on a new collection where I create new rules on Azure Firewall, there is a new thing here as part of the source type. But it used to be the IP address only, but now, excuse me. Now it just shows the IP group as well. So when I click on it, apologies. Now I can just pick that up from here. I can select IP groups here. So you want to just check what it looks like, and then let me just go here, IP groups. Yes, this is IP group that I created. Actually, this is pretty simple service. There is only one setting here that you need to fill up before you use this along with Azure Firewall. This is the place that you add where you add the IP addresses and IP ranges or subnets. As you can see, the CIDR is supported here, in subnet or range or individual IP addresses are all supported here. So you don't have to, you can just, simply put your IP address here, and then instead of those individual IP addresses, you can simply just use the IP group here, so that this one simply represents all those IP blocks and IP addresses in the background. That's a good thing. All right, and this one was the second thing that I wanted to show you today. And then FQDN tags are also here, right? When you click on the FQDN fully qualified domain name tags are listed here. Besides all these things here, HD Inside is the latest one that has been added here, right? So you don't need to worry about the HD Inside IP addresses or management IP addresses that Azure uses in the background for infrastructure management purposes. All those IP addresses are represented by this FQDN tag. So once you just click on it, you don't really worry about HD Inside related things to be included or excluded on Azure Firewall. All right, and what else? And the Microsoft SQL asset. Yes, here actually there is a kind of information here as well. This protocol and port section used to support HTTP and HTTPS, but now it supports Microsoft SQL with 1433 port as well, which is a good thing. That's why I just I wanted to just take it as a positive development, because someday I hope that we're going to be able to use all the other ports and protocols. But this is something. All right, and yes, these are the 4 things that I wanted to show you as part of the Azure Firewall. And all right, let me just go back to Azure Firewall Manager now. Then this is our main objective today. So Azure Firewall, Azure Firewall Manager is a kind of service that allows us to orchestrate the things around security policies and Azure Firewall instances, virtual WANs, which is an important thing that I'd like to discuss today, and what else? Routing management, and even the virtual networks and connections. Right? So you don't really need to worry about taking care of all these individual tasks anymore. The Azure Firewall Manager can be used for all these tasks and management steps. So because there are kind of a number of options to deploy and manage your security architecture, and Azure Firewall is one of them. Azure Firewall Manager here is a really kind of flexible service that gives you a lot of options to deploy your security infrastructure, because there are many different ways to do exactly the same here in Azure Firewall Manager in terms of assigning the policies and creating new policies, converting virtual networks, or creating a new virtual network hub from scratch, etc. So we're gonna be just looking at all these options and which one can be used for what kind of infrastructure.
Oh no. We're getting a few questions in the chat, and I just wondered whether you'd like to keep all the questions to the end or whether you'd like to go through some now. It's up to you.
All right. I think, well, how many questions do we have? Sorry, didn't check
So
that.
there's a few different things. Like, would you recommend Azure Firewall for only external traffic into an organization network or for all traffic? And there's just a few things that I think maybe some questions we could get answered now before you carry on, but it's completely up to you.
I think I'm happy to answer questions that I've been asked so far.
Okay.
Let me just take the first one. I think this is the first one is from Sandy George. Is that correct?
Yeah, 1604.
Let me check. 1604.
I can go through them for you if you'd like.
Well, sorry about it. I'm just trying to.
That's okay.
That's just 4:14 p.m., right? It's just 4:14 p.m. from Sandy George. Is that the first one?
Yes.
Okay. All right. Perfect. Okay. The how does one become a CIDR expert? Well, if you just want to be become familiar with your networking and like a calculations of your subnets, actually there are many things to just start with, but first I really recommend you to just start with some like some core network courses where you can just start learning some subnetting and CIDR infrastructure, so that you can just the lot of math in the background, and then so you can just do some heavy calculations to be able to use. Actually, there are many software out there that you can use to just do that. But if you just want to understand the underlying technology in terms of subnetting, etc., I can recommend some of the tools or services or courses that you can start with. Sure. And would you recommend Azure Firewall to replace an organization's traditional firewall? That's a good question. Azure Firewall is really good for multiple layer. Is it really good for as a multi-layer firewall thing? Because some of the firewalls in the market just allows you to just focus on the like application layer, and some of them are they just like L2 or L3 level. So in terms of Azure Firewall, it's just like more of a network plus threat intelligence plus application side of things. It's just like a combination of network, application, and some like a process things. I would say. So that's really up to you. It's just there is no one correct answer to this question, to be honest, because it's just it's up to your down to preferences, and based on your needs and according to your organization's needs, I think. But this is really good for when it comes to just filtering the applications, or web filtering, for example. If you want to just restrict access to some certain websites from your network, for example, that'd be really great to use Azure Firewall. Or if you want to, if you're happy for Azure Firewall to take care of the HTTP or an HTTPS, and now Microsoft SQL as part of its application protocols, I mean, this is really great. This is nice. Just like out of the box, you don't really worry about the infrastructure and maintenance and things on Azure, because all managed by Microsoft, right? So in terms of the firewall as a service, that's a wonderful thing. But if you are really looking for a kind of device where you can just do some other things in terms of collaborations with other technologies or connecting to other devices, etc., of course, that's a different domain, I would say. The next one is the IP groups are in Azure or on-premise or somewhere else. The IP groups are on Azure now. So yeah, this is a kind of another service now, which is in preview now. So you can simply create IP group, an IP group, and then simply put some blocks of IP addresses or ranges into the IP group, so that you can consume that IP group later when you need to create a rule on Azure. But if you are asking that if you could just use IP group on your on-prem environment, no, because IP groups are kind of different. Another IP group is another service available in Azure, so that you have to use it along with your other services on your Azure Firewall instances. I think there is one more, right? Azure and Microsoft has a reliable or based on experience with. Yeah, that definitely, you know, suggest a hybrid approach in there. Definitely, yeah. Well, you know, they because of the SLA levels are kind of, you know, each SLA has a kind of different criticality level, and then of course a different pricing you know, structure as well. So if you're happy with the 99.5, for example, you know, it has a certain pricing model. But if you have to just, you know, if you're after like 99999, for example, you know, of course it could be kind of a little bit more pricey, but it's just, again, up to your organization's preferences. Okay, I think that's pretty much it in terms of questions, right, so far. So I'm going back to your left.
Thank you.
Thanks very much. Okay, and yes, let's just check the preview features of Azure Firewall Manager here. But okay, what does Azure Firewall do? I mean, what does that give us? Actually, it simply manages Azure Firewall instances, right? But apart from the Azure Firewall instances, it also allows us to manage secure hubs or virtual networks by providing a kind of dynamic Azure Firewall policies, because the firewall policies are also a kind of new instruments that we can make use of as part of Azure Firewall rule management. So in another saying, if you want to use Azure Firewall Manager to manage your firewalls, then you can simply create new Azure policies and assign them to your Azure Firewall instances. So it can create a new Azure Firewall instance, or assign policies to existing firewalls across your organization. It's up to you again. So with the support of hierarchical policies, we can simply bring in parent policies to enforce other individual policies on the firewalls. So with this, we can set the inheritance on specific firewalls, which I can say allows us to control the policy management even more flexibly, because that way different levels of security measures can be used and managed for different needs at the same time. So we can put all of this into CI/CD processes, for example. That's what we DevSecOps guys love, right? So yeah, the other things, actually one of the most important things out there was the security as a service. So security as a service here refers to trusted security partners. That's a new term that we're gonna be looking at today, which provides additional layer of security. Basically, I'll cover that bit later on. This is an optional thing to add on top of existing structure, I could say. So if you just want to use your Azure Firewall along with your trusted, along with your other third-party providers, yes, you can do. Actually, this also answers one of the questions that I answered today. If you don't really have a one single choice here, you can still continue using your Azure Firewall, but you can also enable some third-party extensions or third-party collaboration options along with Azure Firewall, so you can just use them side by side. That's just even in Azure Firewall it is supported. You don't have to just get them connected by just putting some third-party extensions or connectors, etc. So it's just supported out of the box on Azure Firewall. But as of now, there are only 2 trust partners supported, and I'll show you that bit. But yeah, this clearly shows that it's going to be many more in the near future. All right. Okay. Obviously, the virtual networks and virtual WANs are essential elements here, and I'm glad that Azure Firewall fully supports both. And the last one is the split routing. That's just where we manage routing for or branch to internet or branch to branch on the connections. So what that means is simply we can simply say, okay, I'm gonna bypass firewall for this type of connection and keep the others behind it. So that's that's what it is. We can simply say that. So it's just like a more flexible routing than ever. So that's a cool thing. All right. The reason that I wanted to just put this line in here is that these are the services that an Azure Firewall Manager uses in the background. Because it sounds like okay, I'm gonna install an Azure Firewall Manager to be able to manage all the services. No, it's not true. Azure Firewall Manager is a kind of management console where you just create your policies or connect to other virtual networks, virtual WANs, and assign your firewall policies to your Azure Firewall instances. So that's why those 4 services are kind of the elements that we're gonna go use with Azure Firewall Manager. So okay, let me just jump into the architecture types here. When it comes to selecting the best architecture based on your needs, we simply have 2 options here, each of which uses a different infrastructure in the background. But at least at this we know that there are 2 options that I have to just select to work with Azure Firewall Manager, because Azure Firewall Manager works with the either solution. One is a kind of like a bit easier to deploy, but it's like a limited feature. But the other one is, which is Secured Virtual Hub, is a kind of really powerful, fully managed Azure virtual WAN hub resource that you can use with Azure Firewall. So the main difference between these 2 is that in Hub Virtual Network, we simply use standard Azure virtual networks with Azure Firewall. That's it's crystal clear here, because yes, their Hub Virtual Networks are simply virtual networks, right? But in this scenario, it is you who manages the virtual networks. I mean, in Azure Firewall Manager, you just create your policy, and when it comes to assigning that policy to your one of your Azure Firewall instances, for example, you have to just pick your virtual networks and then take care of the the peerings, etc. And then, okay, wait a minute. Well, why would I have to manage virtual networks? Yeah, that's a valid question here. But there are many hubs and spokes in your environment, and that'd be complete madness to try to manage all those virtual networks, connections, and of course virtual network peerings here. But if you don't really have to create and manage a number of virtual network peerings here, or you're not using any secured hubs which are provided by virtual WANs, then there is a solution, I think, which is Hub Virtual Network, because well, if you're not using any virtual WAN, for example, and if you don't have any spokes to connect to your hub network, you can simply just go with a hub virtual network here. It's a pretty simple and clean method of doing a kind of security policy assignment in Azure Firewall. You can simply do the things through your virtual network, because you only have one virtual network at a time, and you don't really want to create virtual WAN and create hubs in virtual WAN and connect all those hubs to Azure Firewall Manager. Well, instead, we just want to go with a virtual network hub, which is a kind of standard virtual network with Azure Firewall. I'm going to show you this one. I mean, this sounds a little bit complicated here, but I'm pretty sure that once we've just seen the options and the scenarios in the portal, yeah, it'll just make a little bit clearer. All right, so in terms of virtual WAN, if you, however, had a look at the virtual WAN service on Azure, it's like a managed hub and spoke model where there are hub gateways and hubs, right? So actually each hub can have multiple connections and networks or spokes. So it's just like a mature a version of multiple virtual networks connected to each other in an automated way, I would say, because this is not possible in a standard virtual network, right? Because virtual networks are standalone resources. Of course, you can create peering between two virtual networks, for example. But what if you have hundreds of different virtual networks, and if you want to use all those virtual networks along with your Azure Firewall Manager, would be a little bit pain, to be honest. So in such scenarios, I'd recommend a secured virtual hub instead. All right. So firewall policies is the next step that I'd like to highlight here. Firewall policy, it's also one of the new services on Azure that we can use to manage multiple firewall instances from a central point. This is the key point here. I mean, because as you all know that the rules and the all the rules, including application security and NAT rules, are kind of attached to Azure Firewall instances. I mean the traditional Azure Firewall instances. But with the use of firewall policy a feature, you can simply use this standalone firewall policy object and simply assign this policy to any of your Azure Firewall instance, which is managed by Azure Firewall Manager, of course. So, I mean, it simply consists of network rules, application rules, net rules, and threat intelligence settings. It's basically all you need in terms of rule collections. But again, this is a standalone object that you can, freely and flexibly use and attach to your firewalls. Also, these are global resources. What that means is that they can perfect the work across different regions and subscriptions. You don't really worry about the region or different subscriptions here. So these policies can be used with both hub virtual networks and secure virtual hubs that we just gone through in terms of the architecture types. So policies can be used by both. So there is a, let me check. Yes. Well, actually, one of the questions that I got recently is whether I can migrate existing firewall rules that are running on a, say, standalone Azure firewall. The answer is yes. Yes, sir. You absolutely can do it with either PowerShell or Azure Portal. You can simply migrate all your existing firewall rules from your existing firewalls. And okay, and another question is like how to create an Azure policy then, and Well, there are several ways of doing that. So you can either create it from scratch or assign it from existing policies, which is called inheritance again. All right, so I'm gonna be looking at this one here. As you can see, this is a kind of comparison table here so that we could see all the differences at first glance, right? Yes, a policy has all the rules and the threat intelligence settings, but a standard rule does not have threat intelligence settings, as they are kind of represented separately on Azure Firewall instances, right? And also, policies can be assigned both to secure virtual hubs and virtual networks, but the rules only support virtual networks. And again, firewall policies are kind of separate resources that you can associate with multiple firewalls across your subscriptions, but it's not the same on the other side. Rules are free because as they are part of the traditional firewall instances, but when it comes to policies, there are different pricing models based on how many associations you make in there. And yeah, both support a number of deployment tools and platforms as well. And okay, this is the rule processing logic. And I'm gonna just show you when I start a demo. So I'm gonna skip this one for now, because it's just like when you create a new network rule or application rule, you may want to ask which takes precedence. I mean, which has the higher priority, etc. So I just want to show you when I just did a demo. That will be much easier to understand. And the last thing that I'd like to point out before the last demo today. So, okay, how are we going to deploy hub virtual networks or secured virtual hubs here? Right, it's just, okay, well, hub virtual networks are considerably easier to deploy because Azure Firewall is the only provider that we can use with that, well, for now. And then, so for hub virtual networks, the first thing that we would do is to create a firewall policy first, and then which is going to done in Azure Firewall Manager as well, and create your virtual network infrastructure. That's the thing that you need to take care of, right? I mean, if you want to have a hub and spoke model with lots of VNet peerings, for example, then you should just do it here, right? Don't forget that all peering operations again need to be done manually because this is all the hub virtual networks can do. So so once you're happy with your hub and spoke architecture, and then all you need to do is to associate your firewall policy that you created to your virtual network. You can either create a new firewall as part of the process, or you can simply use an existing firewall and existing virtual network as well. So right, so you have two options again here. So sure. Of course, you also need to take care of your user-defined routes for routing traffic to your firewall manually again, right? So, but for the secured virtual hubs, here's the sequence again. As you can see, that this is a fully automated and fully managed service here. So it's all managed by Microsoft in the background. This service is provided by Virtual WAN. That's a kind of really cool service that is fully compatible with Azure Firewall Manager here. So that please note that all the peering operations here are also done automatically in the background. So you don't need to worry about manual creations and associations, etc. So this is one of the greatest advantages of using Virtual WAN service on Azure, I think. All right, it's time to do the quick demo for the last thing here. Okay, first, this is the firewall manager. When you just type firewall, there are three things here: firewalls, as traditional firewalls. The second one is firewall manager, and the third one is firewall policies here. So this is the firewall manager. It's pretty pretty clean here, right? I mean, there are 4 sections that represent the whole firewall manager. So the first thing is the firewall policy, right? So in my case, I have 2 firewall policies. Again, these are individual objects, right? So you can simply create a firewall policy here, and then you can, just choose some of the parent policies, if any, and then, or you can just create a rule collections, and just get it ready, and then store here. If you want to assign any of these policies, yes, you can do that. Just click on it, select that stuff. As you can see, associate hubs, remove hub associations, associate VNets, and remove VNet associations. So actually there are 2 things, right? Hubs and virtual networks. Okay, let's go up here to see this, hub virtual networks first. These are the virtual networks. So the thing is that when you create a new virtual hub here, new hub virtual network, sorry, and then it automatically creates Azure Firewall as well. That's the same for secured virtual hubs as well. That's the greatest point, and I think the biggest advantage of using a firewall manager. So if you have a virtual network and you one single virtual network, and if you want to connect that virtual network as part of the Azure Firewall in Azure Firewall Manager, all you need to do is just click on here and then pick your virtual network, and then you can also create a new virtual network here from scratch. So that's why, for example, this is a test VNet 001, right? I created this one using this wizard here. So when I did that stuff, this virtual network test VNet 001 was created automatically by Firewall Manager. Also, firewalls. Also, this test VNet 001 with this FW prefix was also created by Firewall Manager. So that's the beauty of using Firewall Manager. You don't really worry about the creation of virtual networks. You don't really need to worry about creating a firewall instances. All you need to do is just to start this wizard and then just pick your Azure Firewall. You can also use a any Azure Firewall policy as part of the provisioning here, so that you can create virtual networks, create Azure Firewall, assign your policies, and happy days, and you're done with that. That's the same thing here, but the main difference is that this one does not use the virtual networks directly. Yes, they use, but it's not visible to us. Instead of making use of virtual networks as part of this deployment, it uses virtual WANs, which is another solution on Azure, right? So virtual WAN, when you click on it, I have one virtual WAN instance that I had created in advance, so that I have 2 hubs, and then each hub consists of several virtual networks, peerings, express routes, and many other things as well, right? So that's why it's just like a or advanced way of taking care of all kind of hub and spoke model side of things. So that's why Firewall Manager also supports secured virtual hubs as well. So again, one more time, I'd like to highlight that we have 2 options: hub virtual networks with standard virtual networks. That also creates firewall virtual network and policies. And the second option is to go with secured virtual hubs, which uses virtual WANs instead of virtual networks, which also creates firewall and all underlying infrastructure elements in the background automatically. And the last thing that I like to show you here, creating a new policy here again. And okay, let's just say my firm. And okay, rules. I don't want any rule here now. Validation passed. And done. Okay, also, I really want to show you this bit as well. As part of the secured virtual hubs, as you can see there, the second one is a little bit different than the first one, because this has a trusted security partner integration here. So when I click on it and then use the security providers and connections, security providers, you can see there are two things. So that's where we can use Azure Firewall with trusted security, another trusted security partner side by side. So we don't really need to, give up on any of these. So we can simply use those two things together at the same time. But if you want to add, let me remove this, for example. I just add this one. There are only two security partners available now here. The one is iBoss and the other one is Zscaler. Sorry. So as of now, there are two options. But of course, this is where you need to just do the configuration around your trusted security partner settings. But of course, you have to just go to the security partner's website and then do the rest of the configuration out there. That's the only way that you can just initiate your Azure Firewall manager with your trusted partner configurations there. So I think it's pretty much it from myself, and I'm happy to answer your questions, if any.
Thank you, Honor.
Thanks very much.
So let's see. I think we have here one question at 4:51. I don't know if you already answered this one. I don't think so. So sure. What are the challenge limitation with Azure Firewall compared to traditional firewall? So license, cost of ownership, and management, knowledge, access, and control, etc.
All right. Well, yeah, that's a good question. I think one of the biggest limitations in there is kind of ports and protocols supported in applications right now. To be frank, I've been using Azure Firewall for like 2-3 years, and then it used to be like a kind of a bit more of a basic service, but I used to just work with that when I needed to put some application security rules only. I wasn't just able to just get much out of the network rules, to be honest. But now it's a kind of more mature environment, so you can simply use application and network rules side by side. But the biggest limitation is, I think, is the lack of the ports and protocol range, because it only supports HTTP, HTTPS, and Microsoft SQL at the moment as part of application rules. So that'd be really great if they could just add some more ports and protocols. That was a kind of promised thing, but for hopefully we're gonna see that as well. And I think we have one more question there.
Yeah.
How does it work with Azure Bastion integrated or beside? That's a good thing. Well, actually, the Bastion service is a kind of also a kind of separate standalone service that you use when you need to connect to your endpoints without having to use their public IP addresses, right? So that's a good thing. But well, the only connection between Bastion and Azure Firewall will be like network address translation thing that you may want to use with, because the DNAT rules are available on Azure Firewall, that you can simply create some rules where you define who can just come from internet with what ports and what protocols, etc., so that you can restrict access to your endpoints. But Bastion actually itself does all the things by itself without having to require any kind of service like Azure Firewall, etc. Because it's all for just like if you want to use it for RDP, for example, all the things are taken care of by Azure Bastion itself. But you can still integrate some of the virtual network or subnet level security by putting some network security rules instead of Azure Firewall. So that'd be kind of better approach to make use of some network security groups to restrict access to your private subnets where your virtual machines reside, I can say.
Okay, so I think we have no more questions. Can we just close and wrap up? Lisa, are you there?
Yeah, I'm here. I think so, if no one has any other questions. Okay, cool.
Yeah, let's go. Lisa, fire away.
Thanks very much for everyone, and have a lovely rest of the weekend.
Thank you so much
for
everyone attending the Global Azure Virtual Events, and thank you to all who took part, organizer, mods, and speakers, and all the audience to give your time to attend our sessions. I hope you enjoyed. Share any feedback that you have that can improve our work, and we are always available to any questions that come afterwards, so you can feel free to contact us. And I give I hand over to Lisa.
Yep, I just want to say a big thank you to everyone who was involved in the event. We will be all meeting virtually in track 1 for a bit of a hangout and virtual beers type situation in track 1. So if you want to hang out with us, then just click the link in the chat.
Yeah, you're more than welcome. And thank you so much once again.
Thanks, guys. Bye-bye.
Thank you. Bye-bye.